Good morning, friends. This is the second day of mid-year meeting of Indian Academy of Sciences. I welcome you all. Quite important is the talk that my great friend Dr. Ajay Ghosh will be giving. Dr. Ajay Ghosh would be talking on the supramolecular chemistry of windows. So, lot of people have been doing supramolecular chemistry, but what Ajay Ghosh has done in last 15-20 years has made a great difference to our understanding about supramolecular chemistry and the way it should be seen from different angles. Most of the friends who are sitting here, they know he's a member, he's an elected fellow of all the academies, and a lot of awards that I cannot even, I think I will take 5-10 minutes, Ajay. So you please forgive me, I'm not going to, but...
Give me additional 10 minutes then.
Yeah. So what I expect that from Ajay is to tell us how his work has made difference in our understanding about supramolecular. Ajay, I invite you to please come.
Thank you. You give me a lot of hope, thinking that you will talk too much about me, but thank you so much. So, good morning, everyone. Namaste. Let me begin by thanking Professor Varadarajan, the President of the Academy, and all the members, organizers, for inviting me and giving me this opportunity, and as well the wonderful hospitality. I understand that I have my audience today have interest in different domains of science. So I'm aware that I cannot go to the deeper side of chemistry. I will try to engage all of you as much as I can, but maybe in between I'll talk a little bit of chemistry. So you will see the title here. I made it a little broader so that probably you may appreciate it. You may be wondering what is supramolecular chemistry, the non-chemist, and what has it to do with windows. Let me take you to the story now. So this is a slide which I'm sure everyone in this hall is very familiar. We are seeing this every corridor on these sustainable development goals. And every time, we are reminded of our responsibilities as scientists, because all these developmental goals are centered around science and technology intervention. Whatsoever you consider, whichever way that you implement, ultimately we are responsible for the proper implementation. And developmental activities you can't stop, but certain associated consequences we should be aware and try to minimize it. That is the purpose of setting up these goals. And some of the important things, you are aware that we have to provide clean water, clean air, clean energy, affordable housing, affordable health care, of course, waste management. Then we talk about smart city, smart villages. So we have to, being scientists, we have a lot of responsibility to make sure that we are having, because people have the right to live in peace and prosperity, and also should have a comfortable life. So with this brief introduction, let me take you to smart windows. What do you mean by smart windows? I am sure that many of you know what is meant by smart windows. You must have seen many smart windows, smart glasses, because many of the specs that you are using can change the color when you go out in this sun. That is photochromic. There are other type of windows, smart windows called electrochromic windows. Some of you must have seen it in the Dreamliner and in expensive things. But these windows are very expensive. Only Dreamliner can afford, or some other few class of people can afford, but not for the normal purpose. There is another type of smart windows which are thermoresponsive. So I will be focusing today mainly on thermoresponsive smart windows and what chemistry has to do with thermoresponsive smart windows. So this is something which I have taken from Google. You see, if you Google smart windows, you will see many things coming up. So what do you really mean by smart windows, especially thermoresponsive? So hereafter, whatever time I mention smart windows, I'm talking about thermoresponsive smart windows, windows that respond to the temperature. So this is, today we talk about all small, this is a, old-fashioned construction, I think. But today you construct all the new generation buildings where you have a lot of glass facades covered, fully glass. That will bring a lot of aesthetic appeal. You can put different color and you can integrate glass with many, many modern devices, including light harvesting, energy harvesting, and smart way they can behave. So imagine when you have a closed room like this and we are all sitting in this room, and today we have a very bright summer outside. Temperature maybe 39, 40. Not, of course, in Bangalore. And room is closed. Now you can see that sun is coming up. And the solar radiation has many components, different wavelengths of light. And some portion of that is responsible for heating up. IR, near IR, far IR, microwave. And so you have the window. This is the outdoor. And this is the indoor, and the light is coming and it comes out, transmit. Closed, after some time you know what happens. The room will start getting heated up, and then your AC has to struggle to maintain a comfortable temperature inside. That means you are using up energy, and which has environmental consequences. And now how to reduce that load of electricity? So one way is to block that radiation. If you block, then the heating up in the indoor space will come down so that the load of air conditioner will go down. You can save energy. And suppose this happens across our country or across the globe, you can now imagine how much energy that we are going to save and how much carbon footprint that we can save. And that is the whole idea. And here now you can see, this is the window here, and some guy is watching outside. On warm days, what happens is that the window will become, cloudy or opaque, and it reflects back the infrared radiations, allowing partly the visible light coming. So there is a partly light coming in, but IR radiations are reflected back, so that the indoor space will slowly getting cooler. On the other hand, on a cool day, what happens is that the window will be always clear and all the light will come, and the temperature outside is 10 degrees. When all the infrared rays comes in, slowly the room gets warm up so that you will feel a little bit more comfortable. So that is the whole idea of smart windows. And this is a little bit of the science of that, where you see this one, the colored one here is the solar spectrum, where you have the red one responsible for heating up the air inside. And the smart window has to block particularly this portion. If the window is too smart, then you should partly allow this part so that you get some light inside, and you should completely block this part. But it is very, very difficult to design such materials. Mostly what happens is that when the window becomes opaque, then it can block most of the light, and then it will allow the temperature to come down. And you must see that this is in response to the temperature. So there is a competition between the temperature outside and inside. Eventually, after some time, there will be an equilibrium. At that equilibrium temperature, the window should control this radiation. And now comes what is chemistry doing here. And I need not tell you that whatever you talk, whichever way, if you are dealing with materials, you are eventually dealing with chemistry. You have to either you have to use something from the nature available, or you have to synthesize something. And you have to use molecules to make your materials. And these materials, which are smart materials, and these smart materials respond to an external stimulus, for example, heat, voltage, pressure, temperature, so whatever it is. So, and these smart materials, I mentioned earlier that it can be of different types. It can respond to light, it can respond to electricity, it can respond to temperature. And mainly these materials are made up of small molecules or polymers. So you have to synthesize these molecules or materials or polymers in the laboratory. So they are mainly based on molecules. So that is the role of chemistry. And then chemistry facilitates their synthesis, and of course the properties can be tuned by structural modifications. So being a good synthetic chemist, you can manipulate the structure of the molecule, and once you manipulate the structure of the molecule, you are eventually manipulating the properties the way that you want. So you are looking for something and you are trying to build up in the laboratory, and eventually you are going to use it. So that is the role of chemistry on a layman's language. And now again I'm trying to make you understand a little bit more the thermoresponsive smart windows here. So on a cold sunny day, this was I was telling you in my first slide, that on a cold sunny day all the light will be allowed. The window is so smart that it responds with the atmospheric conditions and allow all the light coming in, so that the cold air in the indoor will slowly getting heated up, and that will give a comfortable atmosphere inside. But on the other hand, on a hot sunny day, it partly prevent all the heat generating radiations and allow partly the visible light inside. And see, the conventional thermoresponsive smart windows use certain amphiphilic polymers, though those who are working in the field of polymer chemistry may understand that. And these kind of polymers have an interesting phenomenon called the lower critical solution temperature, which is called the LCST. For example, polyacrylamide and their variants, their different copolymers, they are amphiphilic. They dissolve in water if you put it in water, and initially the solution looks very transparent because the polymer chains are extended due to solvation of the functionalities of polymer by water molecule. But if you suddenly increase the temperature, you break the energy barrier of the hydrogen bonding, the water will be expelled from the polymer chain, and then it collapses to form globules. Once it forms spherical assemblies, then you know the basic principle of light scattering. The Rayleigh scattering or the Mie scattering, it starts scattering light depending upon the size of the particle. And then you will see a cloud coming up in the solution, it becomes opaque. That means you are radiating the wavelength back. So that is the chemistry or physics of that such kind of materials. So this is what is happening. So this is the chemistry. This is a polyacrylamide. Water. You put it in water, get hydrogen bonded, and once you increase the temperature, it becomes globular, collapse the chain globular, and immediately you will see a sudden drop in the transmittance from 100% to 0%. You see it becomes cloudy. So this is the phenomenon that people started using in the construction of smart windows on early days. So it was mainly based on polymers. And now I'm partly a polymer chemist, but I work on macromolecular systems of different types. Mainly in recent times, we have been interested in supramolecular chemistry, as Professor Anil Kumar was mentioning. So we had many different types of interest, especially creating electronically active materials. So we use a family of molecules called pi systems. These are pi conjugated aromatic systems. By virtue of their inherent electronic properties, you can use them for many applications. And so I will quickly take you to some of those, because probably many of you may not be interested in this. I'm just because I'm trying to tell you that, see, our research group, my students have contributed many things in this domain, and that is the reason why we could slowly move away from the fundamental chemistry to a little bit of application at the end of our exercise. So I'll skip all these things, and then, okay, I'll start from here. So now my chemistry friends can enjoy a little bit of the chemistry, others you can take rest for some time when I talk about the chemistry. So this is a classical photochemistry. Don't worry about the structure or anything. I'm telling you, this is a kind of molecules, tailor-made molecules, which is called a 9-phenyl tenyl anthracene. It has a very interesting photochemistry. It's a classical photochemistry. You may read it in the textbook. So we were revisiting this chemistry to understand some of their behavior, especially in supramolecular systems, because supramolecular chemistry can bring a lot of restrictions to the molecular motion, because you are fixing the molecules using some weak interactions. And in that way, you can place the molecules the way that you want, especially to induce certain type of reactions when there are possibility of multiple reactions. So if you want to be interested in making only one type of products out of such combinations, you have to fix the molecules. There are many ways of doing it, creating restricted medium. So one way to do this is bringing the element of supramolecular interaction. So in this photochemistry, you see there are at least 4 different products that you can isolate. But when someone asks you, can you make one among these in greater yield? Yes, you can do it. People have shown that we can make it. So, but we have been using this aspect of chemistry, that is supramolecular chemistry, to make only one product out of this, that is this 4+4 anti-cycloaddition, photocycloaddition product. And subsequently, we have shown that you can do many things with that kind of product. So this is an interesting paper we published in 2019 in Journal of American Chemical Society, where we have shown that you can take the supramolecular chemistry beyond specific reactions, but you can take the product in some sort of applications where we have shown that or demonstrated that you can generate white light from this. We made some devices and all, but there are certain inherent limitations to take it forward. So we did not pursue it much, but the chemistry was so interesting. But then the question came, how best we can diversify this chemistry. So since this photochemistry, which I have shown earlier, was doing in organic solvents, you see, we asked the questions, what happens when do this photochemistry in aqueous condition, because that is the most benign solvent. So I told my student to make the molecules which can be dissolved in water. So we put this kind of functional group. Being chemists, we know what we should do to make the molecules to behave the way that you want. So we made this molecule, and it's a water soluble, and I told the students to look at the photochemistry for what are the products. And then he came and told me, sir, it doesn't work. It's not working. In water, the reaction. So then why it failed in water? It tells you that, because you remember it is working in this condition, in organic solvent, but it is not working in water. So what does it mean? It means that in water, the molecules are not in the right direction. It's not packed properly for these neighboring molecules to interact to form that bond. So that is the reason. Because in water compete with the hydrogen bonding. So the molecule cannot form the hydrogen bond to come closer the way that it is a head to tail arrangement. And that is not possible in water. It takes some other. And you see this is an amphiphilic molecule, and the organic part hate water. Only the side chains like water. So they are exposed to outside. The organic part will go and hide somewhere inside. So it cannot have this kind of an arrangement, so it cannot give this product. But in organic solvent, it organizes in this way, and it gives this product. But when the student came and told me that it doesn't work in that concentration, I told you increase the concentration, and then see whether when you have more concentration, probably it may organize. Then he came and told me, sir, it doesn't work. I cannot dissolve the molecules in water. When I'm heating, I'm getting a cloudy solution. Okay. So then we thought this is something interesting. The molecule has some other properties. So the full credit goes to the student. He has observed this and he has reported me properly. Otherwise, sometimes what we do is, okay, that reaction is not working, I'm not going to work it, so throw it. But he didn't do that. He started investigating in detail. So this is what I was telling you. This is the LCST phenomenon that certain polymers do. And now we are observing it in small molecular systems. And when you heat it just above 32 degrees, immediately the clear solution turns opaque. And you have two phases. One is the turbid phase, and the other is clear phase, which is a concentration dependent process and temperature dependent process. It is a reversible process. There is a small hysteresis between the heating and cooling. These are the properties of the molecules, and we have done a detailed investigations. So it is obvious that it is showing this property because of the phase change. And phase change means, the conformation is changing. Eventually, it is becoming globular to reflect the light. So this is what is happening in terms of a cartoonic style. So this is the molecular structure. When you put it in water, this is the hydrophobic aromatic part. It comes and hide inside, and the other hydrophilic portion will be outside. It forms small disc-like nano micellar structures, which stack to form small nanorods, very, very small nanorods of 10 to nanometer. That is what you see when you look at the dynamic light scattering. You see initially this is what you see, less than 10 nanometer small aggregates or particles. Okay? And you can see, if you look at the correlation diagram of that, you see it doesn't follow the basic principles of light scattering, which means that these particles are not spherical. Okay? But if you increase the temperature, this is what happens. Suddenly you see the particle size is growing up and it becomes micrometers in size. And then you look at the dynamic light scattering correlogram, you see a perfect sigmoidal correlogram, which says that the particle has now spherical shape. And that is why it's scattering light, and that is why you are getting the opaque solutions. So in cartoon, this is what is happening. So it's at a small nanocylinders there, or rods there, that can allow light to come in, and it is transparent. And when you increase the temperature above the LCST, all these small nanorods is expel the hydrogen bond of water outside to the away from these molecules, and they start aggregating, and they form sort of a globular or spherical aggregates which start scattering the light, and that is why you are getting this phenomena. And then we have done it, we have made the photo product of this by radiating light with light appropriate wavelength, and we also looked at the property of those kind of photo products, and they are also showing the same kind of properties with a little bit of variation in their LCST behavior. And now this is the photo product, so a little bit of chemistry here, and don't worry about all those things. So the photo product also has the same kind of chemistry. Okay, I'm just skipping all these things, but finally, what you can do with this? The eventual objective is what we can do. Whether you can replace the conventional polyacrylamide with these kind of systems. So we started making some prototype windows of small 10 into 10 centimeter square, as you can see here. Initially, it is a transparent window. It is a little bit colored because the molecules are conjugated. There is a little bit of absorption of light there. And then if you heat it, you will see that when the temperature goes above 32, that is above the normal room temperature in the tropical climate, you see immediately it turns to opaque. It can block light. And these are the thermal images, outside and inside. Outside and inside. Inside, you see it is temperature is, I don't know, 35 point something, and the outside temperature is inside temperature is 27 and the outside temperature is 32. And so this was actually patented and then subsequently published. So this is one aspect. Now after seeing this, we really got excited, and then we wanted to generalize the whole thing. And what are the type of molecules that you can bring in here, and then how best you can tune these properties. Because once you are looking for applications, people will ask a lot of questions. Whether you can control the transparency, whether you can control, because different places have different kind of climate, whether you can customize your window. So of course, again, I should say, being a chemist, we can play around with the structure of the molecules because the power of functionality is so, interesting. So we started making different kinds of molecules. Of course, there are fundamental interest from the photochemistry and other chemistry point of view. At the same time, from the smart window point of view as well, there are a lot of interest when we look at these type of molecules. I'm skipping it, and how much more time left, Anil?
Yeah, you have 13 minutes.
Oh, 30 minutes here. Okay. So I think I can stop it on time. So again, this is another type of molecules. Instead of these cycloadhesion reactions here, something called isomerization. Many of the chemists know what is meant by photoisomerization. There is something called the cis-trans isomerizations, EZ isomerization. There are different types of isomerizations. These are mainly, happened across a double bond. And you can easily follow by recording the spectral changes, UV visible spectral changes, and by other methods. So these molecules, we have done detailed studies. You can make different kinds of products out of this, but this chemistry can be controlled by controlling the reaction conditions. Suppose you want to see, initially if you take these molecules and irradiate with a certain wavelength of light, there is a flipping, isomerization, and the property of this molecule will be very different from this one. So then if you do further photochemistry at certain conditions, for example, in presence of oxygen, if you do it, then you have a bond formation here, and you close that, and it's a ring annulation to form a extended pi systems. But if you don't want this, you can stop it here by doing the chemistry under appropriate conditions. And the point is that since these molecules are LCST active, you can have different LCST temperature out of this chemistry. For example, this molecule has an LCST transition temperature of 33 degree, whereas when it undergoes isomerization, reduces to 28 degree. And further, if you do this ring closure, then the temperature changes to 30 degree. So you have the option now to manipulate with the LCST behavior by doing chemistry under controlled conditions. And that way you can make materials which are responding at different LCST temperature like this. So each of these molecules has different LCST behavior. And by using these kind of materials, you can now apply the combinatorial approach. You can make libraries of molecules and then libraries of windows. At the end of my lecture, I will show you how you can make libraries of windows using. And this is again how we follow up all these reactions using, on this phenomenon using dynamic light scattering and other available, experimental techniques. So this shows that, when you have different products, you can see that their LCST behavior is now slowly changing. You can from higher to lower temperature by making different products, and you can see that it is, it can be cycled any number of times, and these are the response times. It has, a response time of 12 to 20 seconds. Within that, it undergoes the phase change, and that also everything can be modulated by changing the structure of the molecule. And again, I'll show you one prototype window here with these molecules. One of the molecules, you can see that it has a very clear, transparency at 25 degree. But if you increase the temperature, it becomes completely cloudy. And so you can go to any number of cycles, 1,000, 10,000, 20,000. And now we have windows sitting in our laboratory even for the last 5 years. So you may wonder, organic molecules, will it degrade? If there is a possibility. That is one of the difficulties of dealing with organic molecules. But you must remember that now we have display which is made up of organic molecules. I remember when I started my career at some 30 years back, that time this display organic light emitting diodes and other display devices were coming up in a big way. I remember many of those leaders giving lectures and many of the people sitting in the audience asking questions, how long these will survive. Will it survive for 1 day, 2 days? But today it can survive 5 years, 10 years in the device. So the technology has improved. So if you ask this question, what is the stability, whether it can be used, my answer is the same, that it can withstand if you properly package it well, protect it from air. And another use of intention of using photoresponsive material is that such materials, when light comes in, it undergoes some reactions and it prevents degradation. It's only product change, A going to B or B going to C, but it never degrades as fast as other organic molecules. So you can then increase the lifetime of the molecules here. And again, so this is again a cartoon way of the mechanism of operations. This I have already explained what is happening in this, so I'm skipping it. I will show you one video. Hopefully it will work, because I have been telling you so many things, and once you see it, probably you may believe me. So this is a window. Now it is heating. Initially it is transparent, and you see heating. You can see the temperature here is, if you can't read it, I will read it. It is just 31 degree. It has suddenly become opaque, and you cool it. It has gone to 27, 26.9, and when it comes to 26.5, started becoming transparent, and when 26.3, it becomes completely transparent. It happens in a few seconds. So the point here is that this is the cheapest way that you can make a smart window. Whereas in electrochromic systems, you need a lot of electronics to control that. You need electrolyte, you need special glasses, ITO glasses, and all these kind of things. Photochromic means you need expensive molecules to make it photochromic. And photochromic, have other inherent limitations. Whereas this is the simplest thing. You don't need anything. 2 glass panes, 1 mm gap, make a solution in water, 1 millimolar, fill it without air bubble, seal it. That is what you need. You can fix it windows. And it should work when the temperature outside is 33 or 32, it should immediately turn to opaque. And then you have a little bit of air conditioning here. There will be an equilibrium, and the equilibrium temperature may be something like 26, because 26, 27 is comfortable for us here. And at that temperature, it may remain transparent or opaque depending upon, but it is dynamic. So it is kind of an autonomous. You don't have any manual controlling system. It goes with the climatic condition. And so that is the beauty of these kind of things. I think I have one more windows. This is the window which is made up of the molecules which I showed in the later part of my lecture. But it is manually heating with an air gun. You see the temperature is 30.9 here, around 31, it immediately becomes opaque. And once you cool it, you see that it started cooling down from here, and immediately, it can become transparent. So now the material is patented. We are negotiating with some companies who can make it practical, but there are a lot of, the difficulties in going for a viable product. There are a lot of questions how to engineer the whole thing. But I think, if you look at the way technology is maturing, I'm sure that at some point of time, we may be able to, or someone may be able to put it in practice, and you may see buildings having fully complete windows, glass windows, where you have these kind of cheap materials being used for energy saving purpose. And now the idea is how you can customize. People may ask, I don't want too many darkness, too many, and also white and black is always monotonous. We need a little bit of aesthetic appeal. So can you make colors? Okay, you can put some dye inside and make colors, but that is not the way. You should have molecules which are having different types of colors absorption. So, and also it should be light colors. So yes. So now we are making molecules of different characteristic, different absorption and stability and all. Now you can make windows. See, this is a window which is responding between 24 and 28 degree, which is the most sensitive to the lower temperature side. So the ambient temperature here is between this. You can have this kind of systems. And then it remains opaque at higher temperature. So it has on-off state. But if you have this molecule, it's a different molecule from that, you have different color, okay? But you see 24 degree, it is transparent, 28 degree transparent, 32 degree transparent. But after 32, you start becoming opaque. So that is responding at a different temperature range. Now, the beauty of supramolecular chemistry is, I didn't talk anything about supramolecular chemistry, but beauty is that you can now allow the molecules to self-organize in different composition between these two. For example, you have A and B. You can mix this in different molar ratios. And then you can tailor the property in between this. That is, in between 24 and 38. You can make windows which are responding in between any of these temperatures by simply varying the mole ratio of this. And now you have, for example, 1:1, you mix it, this is the response. Up to 28 degree, it is transparent, but when it crosses 28 degree, it becomes opaque. So now you have windows which is responding to 28 degree, 32 degree, and 38 degree. Now you can apply, you can make modules with all these, and you can mix the modules, mix and match. You using the combinatorial or permutation combination method, you can make any number of, depending upon the total area, you can now combine this. And then you can get windows like this. You now look at, these are, for example, when I have these kind of modules, different modules, it is, initially it is transparent at 25, but when the temperature outside moves to 29, you see only one of the module is opaque and other two are transparent. So it partly allows light to come in, so partly block the light. Okay, so it can partly control the temperature. But again, the outside temperature, because from morning to mid of the day, the temperature will go up, and the midday it can be very high temperature. But when it becomes 33, you see two of the module become opaque. The other one remains transparent. So you will get a little bit of light. But again, if the temperature is going beyond 33, you all become transparent, opaque, it completely blocks the light. And now you can use these combinations and create any number of windows. So I'll stop here by saying that there are a lot of options now to make such windows. So finally, I think it's time for me to conclude. And whenever I give lecture, I show the photographs of all my students because each one of them have contributed in some way or other. But the work I discussed today are mainly done by these two Bengali guys. They came to me thinking that I am a Bengali, but unfortunately I am not a Bengali. So
wonderful.
I should give me a few seconds. So I'm now in SRM. I retired from CSIR. Last 1 year I am in SRM Kattankulathur. It's a huge campus, a very nice place. We are giving a lot of importance to research and high quality science. And I'm very happy to be there. And I'm sure that you will be also very happy once you visit there. So I'm extending a warm invitation to all of you. Whenever you are in Chennai, please give me a ring. I'll invite you there. Thank you very much.
Thank you so much, Ajay. If there are any questions, concerns, please.
There is one question. I'll take that and then I'll come back to you.
I have a comment and a question.
Yes.
When I also heard your name, I thought you were a Bengali. Then when you started talking, I thought you were a Malayali.
Malayali.
Good.
Yeah,
so I was right.
Yeah.
So my question is, does nature use this for photo protection, for example, in biology? This kind of, is it being used in biology? Nature is very clever.
Yeah, nature is very clever in many different ways. But the one which I am talking, this is, I think you don't see anything in nature of this kind. I don't know whether there is some living system which can change their transparency by...
Like beetles and so on.
Beetles and all have other physical phenomenon. Like, for example, what you call the structural colors. They can change colors. They can probably also change some other, for example, softness or shape. But I haven't heard anything which can change the transparency. I think Sriram maybe know it.
I have a sort of negative answer, which is, of course, nature uses it in one way. Cataract is because of protein aggregation, the opacity of cataract.
True,
so it's a bad case. Yeah.
So that probably one good example, Thank you so much.
Yes, yeah, please.
Thanks for nice lecture. I have two questions. Response time is very quick actually. If you see these other stimuli response materials, it takes much time to convert one form to the another form. So here, what strategy we need to adopt to respond the material very quick? Because see the temperature 28 to 33, this aggregation and deaggregation. That's
yeah, because actually the chemistry is like many of these chemistries are very fast. It can even happen in femtosecond.
Yeah.
Isomerization. But here we have seen that when you take the solution in bulk, it takes few seconds, because we have seen that within 20-50 seconds it undergoes the isomerization. But the other phenomenon which is responsible for the phase change is a temperature sensitive phenomenon, which is not that fast as photochemistry. Okay, but still it is happening within seconds, like 16-20 seconds. I have shown the response time. So, but it's very, you see the transmittance is coming down very quickly within a difference of 0.5 degree or 1 degree. Comes very fast. So it is pretty fast, these changes.
Okay. The another question, actually recently I saw some recent literatures. This thermal response material people are using for the energy harvesting, particularly the thermal energy harvesting. Can you comment on that?
Those are photothermal or electrothermal kind of.
Because it's when it's absorb the light, it transformation, then when it cool, then reverse back the original, then they release the energy.
Yes,
that energy
materials have many different types of applications.
Okay.
So you say, what you were saying is photothermal materials. They like it's energy harvesting. For example, waste energy harvesting that is coming up in a big way in waste energy management.
Sir, very nice presentation. I am from biology, but the talk is very interesting. So I want to ask, because if you use this in a room or any place, it is 6 to 7 hour heat, and then again the cooling things. So what is the durability of your system for you can say sustainability of your system in real sense?
You mean shelf life?
Yes.
That is what I was telling you. Look at the sustainability of organic display devices or any organic electronic devices. They are staying. Of course, they are.
But
they are packed very.
Putting in a room,
yeah.
changing the wall is with the glass is not easy task like changing AC.
No, it is very simple. What you need, windows. It's just like, for example, this glass window. How difficult it is to put this glass window there?
Okay.
Only that same difficulty. The only thing which people have to be careful here is that you are putting some liquid inside and you have to seal it. There should not be any leakage.
Okay.
But here it is water, So water is a benign solvent. And the molecule is using in a very small concentration, It is in millimolar concentrations. So you don't need bulk, molecule. If you have 1 gram of your material, you can make several windows.
Okay, thank you.
Yeah.
I have a small question. Without making opaque, can you have a difference in temperature, make it transparent?
That is why, depending upon the structure of the molecules, you can have transparency at different temperature, right. Or even varying the concentration, you can control the transparency, because the transmittance of light also depends upon the concentration of this phenomenon. Okay. LCST phenomenon is a concentration dependent property as well. So if you decrease the concentration, you can slightly control the transparency. So there are many ways you have to fine tune for your requirement.
See, the thing is, the property that you talk of opacity and transparency. Remember, this is highly temperature sensitive. 7 degree. Will it limit the application for tomorrow, or will it make it better? These are the things that I am sure Ajay's talk will throw lights on, and we will be greatly benefited. And thank you very much, Ajay. I think I am taking you granted after 4 questions. Thank you so much.
Thank you.
Wonderful. I'm delighted.
So, thank you, Professor Anil Kumar. And with this, we go on to the next talk of the session, and that's Sudipta Maiti. So, Sudipta was in TIFR Mumbai, and now I believe he's in BITS Pilani, but I think it's the Hyderabad campus, if I'm not mistaken. So, he's going to be talking about instrumentation for molecular biophysics.
Good morning, everyone, and thank you very much. Okay. Stripes are fine. Okay. Yeah, good morning, and glad to be here. My talk is loaded. Thank you for the invitation. Good to see many old friends, some new faces, and I'll talk about molecular biophysics, and I'm currently at this place, fantastic place, BITS Pilani, Hyderabad. They're also like SRM that Professor Ajay Ghosh talked about, are building up big in science and deep tech, and that's why I'm there. And till very recently, most of the work that we'll hear about is done while I was at TIFR Mumbai. And what I'll talk about is one sliver of the stuff that we do, but I will try to connect it to the requirement, I would say, of experimental scientists to build their own instruments. And I think I can't stress that enough. And as I go along, I'll try to point out where these things were required. Before I start with that sliver which will be on membrane, let me quickly run you through some of the stuff that we do, because many of people here won't know me. So this is a great opportunity for me. protein aggregation, which trying to find out the molecular mechanism of neurodegeneration such as Alzheimer's, Parkinson's, or non-brain things such as type 2 diabetes. They all happen because the causative agent is supposed to be protein aggregates, not viruses, not bacteria, protein aggregates, your own proteins aggregate. And this molecular mechanism has been fascinating to find out, and it's still, of course, a work in progress. And throughout many years, I'll concentrate only more last 3-4 years, but for many years we have been working on it. Where we came, okay, this paper is now published. Where we came to is we looked at how they start to aggregate when they first form the small aggregates, oligomers. And we always thought, because there's a missing piece of the puzzle every time we went in, either in vitro or in cells, that it cannot be just this one thing, because nobody can really reproduce in the test tube what are the conditions are there in the brain. It doesn't, even the logic doesn't apply. The concentrations that you require for aggregation to happen in the test tube are orders of magnitude higher than what is there in the brain. So I always thought there is a partner or partners in the brain that even biophysically, if I put it that back in the test tube, will show the same thing. So finally, last year we got to that. Sorry, the reference is missing, but this came through this ApoE being the partner. Other thing that we have been doing for a long time is building microscopes to look at how the brain functions, especially brains, parts of the brain or brain cells which give you feelings of reward, and it gives you a high when you're doing drugs. I mean, I'm not saying you, in general, when you're doing drugs. And we always wanted to find out why that is happening, how that is happening, what are the other changes that are happening in the neurons, and nobody had a way to look at the main molecules, the neurotransmitter molecules here, 2 of them are there, serotonin and dopamine, how they go about in a living cell. There was no way of seeing it. So that we developed over the last few decades, and this is one of the, used to be the mainstay of my lab. Developing microscopes still is, and I'm developing a new type of microscope now, no longer looking at the brain, but looking at cancer tissue that I won't get a chance to talk about, but these sort of made the background that one can build a UV microscope to look at cancer tissue very fast, hopefully intraoperative, and something that has not been done anywhere in the world, but hopefully we are close. The stuff that we'll talk about is membranes, so I would come back to it and not spend time here. The other thing that we talk about, and sometimes talk to Raghavan quite a bit about this, is looking at peptides and self-peptides. Take a piece of a protein, present it to itself, of course stabilized in a conformation that it looks like it does in the protein. So if you take a piece of the protein, it no longer looks like it because it sort of unfolds. So you keep it folded chemically, and then wonderful things happen because this protein recognizes this self-peptide, and we are having a lot of fun with it, making protein silencers with this self-peptide, and probably have a chance to hopefully, at least in a laboratory, go to antibiotics. This is the other thing that I said is developing technology. Many of the research that we have done, there's always been an element. I've been trained as a physicist, doing some biology, meddling in some biology, and used to head the chemistry department in TIFR. That's sort of as interdisciplinary as you can get. But it has been, heart has been my training as a laser spectroscopist, understanding optics and laser spectroscopy and building tools. That's been a passion, and we have done it over the years. We have taken, I think, as I said, I believe that we experimentalists in India, we need to start making our own tools. As many of you do, heading some department or something with applications, people are saying, okay, I need an instrument that costs 4 crores, 5 crores, 10 crores. I go back and ask, can you build at least part of it? Do you understand it well enough? And people who are very good scientists, they publish very well, unfortunately do not understand their instruments. And this cannot go on in 2025, given the geopolitical situation and the economic situation. We must start building our own instruments. We've started doing that in a little way. Not the ones that are saying that, hats off to those which says, okay, much cheaper, etc. But I'm talking about things which the world doesn't look at because it's cheaper, because it's better than what can be done. So some of these instruments, fledgling efforts, But now I'm going in a much bigger way. And I also started teaching people who, students who would become tomorrow's scientists, knowing how to build these things, break the instrument apart, put it back. And this has been going on now, the 16th year now, something called FCS. Started by teaching people how to build this instrument, but now it's much bigger, all of fluorescence and Raman microscopy. Now, lots of my friends from all over the world and in India run this. And, about, 1,500 graduate students have gone through this. Many of them have done wonderfully in building methods, instruments. Unfortunately, not so much in India. They have all gone abroad, etc. But this is something that is very close to my heart, and we keep doing it. Okay, so come back to today's talk and talk about membranes. So for those who are not biologists, I understand, and there are some, I met a doctor on the way here, some who are on this side of the spectrum, some are on that side of the spectrum. The cell has a membrane, which is a barrier that separates it from the outside to the inside, okay? And it also has internal membranes, which are barriers which allow it to do different chemistry in different locations inside the cell. And that chemical organization, ultimately what makes life. So it's very important as a barrier. So you can think of it as a wall. But if I tell you that you're building a wall, then you'll say, okay, give me some regular sized bricks and I'll build you a nice wall, because they need to fit with each other properly. And I tell you that nature has, and if you'll pick the right kind of brick, but you will not mix and match them, because it's going to be a very tough thing building a proper wall if you mix and match them. But the bricks that nature uses for building these walls, the membranes, are of 200 different kinds. And I dare say nobody really understands why we have so many types of bricks here, the chemical bricks, let's say the lipid molecules, cholesterol being one of them, and other things. Why you have so many? I mean, it's very difficult to make some arrangement if you just throw in randomly, quote unquote randomly, many different things. And this has really been my passion to try to understand this over the last 4 years or so. And the answer, of course, that it's just not just a brick, we are not making this barrier just to make a very solid barrier, because the barrier that life has between the organelle and the cytosol, or between the cell and outside, has to do many more things than just making a brick wall. So this is a molecular level cartoon of a membrane. And you see there are different types of lipid molecules. There is a lot of disorder in this. There are other things. Other than the 200 types of lipid molecules, many types of proteins, membrane proteins, and stuff that we have started focusing on the last 4 years, many small amphiphilic molecules. Just heard about amphiphilic molecules from Professor Ajay Ghosh. These are biological, natural amphiphilic molecules, and people have neglected the fact that they can go in at very high concentrations into the membrane and perhaps change its properties. People, of course, there have been many Nobel Prizes on these things, which are proteins which are there in the membrane, including how they allow the membrane to do some of its function. Thomas Sudhoff got his Nobel Prize looking at endo and exocytosis, how some proteins in the membrane and other proteins actually help that process. So it has to do, so the membrane is not a brick wall, because it has to do many things, including something that we'll focus on is endo and exocytosis. Endocytosis is the membrane invaginates in and takes things inside the cell. Exocytosis is there are already preformed vesicles, balls of chemicals which go out, and this is thrown out to the outside world. We need to talk, we need to communicate, then that makes us human, and the cells need to communicate to survive, okay? Both transport and signal communication, transport of material signal communication is very important. And cogito ergo sum, I do exocytosis, therefore I am, because in the neuron, when you are listening to me, this is exo and endocytosis processes are going on all the time. Not only in neuron, it happens in all cells, but signal transduction between neurons happens primarily through chemical means. These molecules which I mentioned, such as serotonin, they are made inside the neuron, they are packaged in a vesicles, which is also a membrane limited compartment, goes to the outer cell membrane, it has to open it up. and throw out that thing when it needs to, quote unquote, talk to the next neuron. So the question that we have been asking is that the membrane composition, many of us take cholesterol lowering drugs. Cholesterol lowering drugs because that is inhibiting the synthesis of cholesterol. Question is, what does it do? Because it will probably change the membrane composition in some way, and does it affect other functions of the membrane? We are all happy that its cholesterol is being lowered, but what else can it do? That's a question that I'll give you a little bit of an answer to, a slightly disturbing answer, but anyway. So you see these little, so these are molecules, they're in the molecules, of course, are not to scale. They are in something called vesicle, and this process, this vesicle, one of these has gone in and has merged here, and this is the process of exocytosis. So we are very interested in knowing how does exocytosis get controlled. As I said, Thomas Sudhoff and others got a Nobel Prize telling us how proteins control exocytosis, how chemical signaling with calcium causes exocytosis. But this story doesn't take in the fact that there has to be, the membrane has to be pliant enough to do it. If I make a very strong big brick wall, it's very hard to make a hole through it. So nature has to make it pliant enough, and whether these small molecules, which are anyway part of this, are playing a part in making it pliant enough, including the neurotransmitter that's inside. Okay. And we started this work about 4 years ago or so, and not too many people are thinking about it. Now quite a few people are thinking about it. So I took my privileges as the executive editor of physical chemistry to commission a special issue, because there are 36 accepted articles already coming up next month. So if anybody is interested, look at that virtual special issue. Okay. So quickly, what questions are we asking? And can small, how much time do I have? 7 minutes. Huh? 7 minutes, okay. So 4 quick questions. Can small amphiphiles change the properties of lipid bilayers? This is something that has been neglected. How does that affect other things that the membrane has to do? The vesicle association, fusion, and membrane protein dynamics, properties that are different from a brick wall. Is this relevant for living cells? After all, that ultimately what matters. We'll find it out in artificial bilayers and look at it in living cells then. And then finally, can we find or design molecules which are able to do this? Then I have molecules which only talk to the membrane, not to any of the proteins. They're quote unquote bioorthogonal except for the membrane, but I know exactly how they change the properties of the membrane, so I can control exocytosis, endocytosis. Can we? That's the question. And the example molecule is serotonin, which is a natural amphiphile. So first question, can small amphiphiles change the properties of lipid bilayer? When I say properties of a bilayer, it's a very complex object. Which property am I talking about? And we also didn't know what property to look at. So we targeted about list of 9 properties, and we had to build an instrument which can measure all those 9 properties, or most of those 9 properties together on the same membrane at the same time. So this is where again I say that an experimentalist should be tools. There are undue advantages that you get for doing it. There is an AFM, atomic force microscope, confocal microscope, fluorescence lifetime imaging microscope, and fluorescence correlation spectrometer built by my students, not by me. And other techniques such as solid-state NMR, this work has been frequently in collaboration with my very good friend Daniel Huster. So he does solid-state NMR. So this is AFM image, the solid-state NMR, order parameter measurements. Sorry, you don't have time to go into this, but the point is, if you put few millimolar serotonin, and few millimolar is not very large. I have to finish quickly. You have 250 millimolar serotonin packed in your vesicles in your neuron. So it does affect the mechanical properties. It does affect membrane order, does affect how easy it is to make a pore in the membrane. It does affect membrane protein function by changing, not talking to the protein itself, but talking to the membrane and doing some kind of membrane mediated allostery, and changes the functions of GPCRs in the membrane. And it does change the ability of vesicles to fuse. This is sort of a mimic of exocytosis in a test tube or in a cover slip artificial system, and you see that it changes the rate at which vesicle fusion happens. It may not be only the proteins which control it, okay? And the cautionary tale that I said I will say is that if you reduce cholesterol, somehow the ability of the membrane to make a pore reduces. So your ability to do exocytosis actually reduces. I'm not scaring you, but there is a recent report in Britain looking at 5,000 cases of people who are doing statins for the first year, and the intellectual ability goes down. It recovers over 7 years, which is interesting because body has this thing. So don't be too scared. But we are trying to find out the mechanical origin of this, and this may be something. Is it relevant for living cells? Yes, it is. We looked at serotonin and membrane order in vesicles by again building a very new kind of microscope, and we found that if you look at membrane order, these are neuronal cells in culture, and you see exocytosis after inducing exocytosis. The vesicles are the yellow, they go out and they become stiffer. G by R is a measure in a spectral microscope of how stiff the vesicles are, and this is with time it goes down, the stiffness goes down. That is, less stiff vesicles are getting released more preferably. So you need to be pliant enough to be released. Last question is, can you find molecules which are able to do this effectively without talking to others? We started with something which is a psychedelic. Okay, there is something that needs a license for large quantities and for any quantity in Germany, so Daniel couldn't do it, and we could. Small quantities are available here, and Kaustubh Mote did some solid-state NMR. We found out that we start with the psychedelic, which is of course not bioorthogonal by any means. Try to understand the chemical nature of why this psychedelic is actually 100 times better than serotonin in perturbing the membrane. It can perturb it at micromolar level. So we went through many molecules looking at these 9 parameters and a set of parameters, trying to measure where they go in, how much they do, what they do, why they do it. And we have some sort of quasi-bioorthogonal molecule, NAS, N-acetyl serotonin, this which seems to be a starting point for us to think about how to make a molecule which can do many things, make the membrane plastic without talking to any of the receptors. So this is what I told you. Can small amplifiers change the properties of lipid bilayers? They can. All these can be, can these affect function of bilayers such as vesicle association, fusion, etc., important for exocytosis, endocytosis, that they can, and this is relevant for living cells. I just showed you some cell pictures. And can you find the chemical logic of why some molecules do it and some molecules don't, or they do it in orders of magnitude different efficacy? And I think the chemical logic is emerging, so that new class of drug molecules which work solely by membrane modulation is in principle possible. My last slide is that we had to build a lot of instruments, and this is hard to do in India. Over the last 2.5 decades that I've been here, it's extremely hard because the little screw that you need will take 3 months to come. But we still need to do it. We still need to encourage people, young people who are coming in to do it, because there's no longer time that you can just ask for a 5 crore instrument and produce some papers with it. We better make our own instruments, as whoever can. And you look at China, every time I go to China, it's just mind-blowing by what leaps and bounds they're progressing. So let me just thank my students, my collaborators. I don't have time to name them, but the 3 ones are the Ankur Gupta, Deb Shankar, and Ankur Chaudhary, 2 Ankurs and Deb Shankar, who did this membrane work. Funding has come from different places, and my collaborators are there. And I'll end it with things that I would not talk about, but I exhort you to think about this. Technology, and build a community. I've just started doing it in BITS Pilani, and hopefully you'll give a platform like I did by starting the conference. An industrial platform, you come in with your ideas, go out with a prototype. If it's something optical, do talk to me. Thank you very much.
Thank you, Sudipto. Fantastic talk, inspiring as always. We've got time for a couple of questions.
So a totally technical question. You said G by R is some measure of stiffness. It's a purely optical microscopy-based measure. How does that, what do you do?
Okay, sorry I didn't have time. G is green, R is red. It's a spectral shift of a reporter molecule that goes into the membrane, and it becomes stiffer when it becomes greener. So
I see.
the spectral shift, and you can measure it in the microscope while you are measuring serotonin concentration, etc. that we built, but G by R, and we can look at individual vesicles going out. So we can say, okay, that guy has that vesicle's name is Shriram, and that has a G by R of this. Its probability of exocytosis, is it large or not? That is clearly correlated with the G by R thing, which also is correlated with how much serotonin it has in the membrane.
Nice. Sorry, is DOI a well-known psychedelic? Does it have a market name?
Okay, so DOI itself is not so good. There are things, have you heard of magic mushroom? Yes. So yeah, so magic mushroom or psilocybin is in that family, and DOI is, it probably doesn't have too much market value because you have better things. Okay.
If there are any other questions?
Yeah, nice talk. So I want to know, you mentioned that the concentration of serotonin itself affects the exocytosis phenomenon. So what is the mechanism? I mean, and do you think it's true for the other neurotransmitters as well?
Very good question, thank you. I think it's true for the monoamines. And I think there is a very good reason. Of course, I am just guessing here, which is the monoamines have a tendency to go into they're very amphiphilic. They concentrate in the membrane, and they are known to have after effects. They are neuromodulators, and they are not just point to point, millisecond to millisecond communication thing. When neuromodulation, serotonin, for example, is in the pathway of depression, and what Prozac does, which is an antidepressant, is actually increases the population of serotonin in the extracellular space, where it can go and sit on the membrane. It partitions into the membrane phase about 1,000 to 1 from the thing. So I think, and dopamine to some extent also does similar things. So I think these monoamines have, the neurotransmission due to monoamine has a long-term memory in the system, and that's why it's neuromodulatory, not just neurotransmitter. I don't know if that answered the question, but I'd love to talk to you later about it.
Sure. Shona?
Yeah. Hashidutta, wonderful talk.
Thank you.
Are you suggesting that the increased ply nature of the vesicles would also increase drug efficacy eventually in terms of delivery?
Yes. So if you modulate the nature of the vesicles, the mechanical properties that you can actually measure, I think it will absolutely also modulate the effects of drugs. Absolutely. Yes. That's exactly what I'm pointing.
Sudipta.
Sorry.
Yes.
Hi.
Pleased to hear about building your own equipment. But when we're talking about AFM, solid state NMR. Can you just give some more clue about what fraction of it is home built and what is bought?
Okay, you are asking the technical engineering question.
No, it's
so that
I am all for building your own equipment, but just when you say AFM, was it bought or was it made?
Yeah, so it is AFM, atomic force microscope.
Yeah.
Confocal, which is a type of fluorescence microscopy. Fluorescence lifetime imaging, which tells you the fluorescence lifetime, you know about limb, and FCS, which is fluorescence correlation spectroscopy, which tells you about
all of it was built here, or you bought some of them, and that was the...
What, sorry?
All of it was built by you, or...
All of it means, okay. Let me characterize that thing. When I say building, suppose I want a PMT or this thing, I don't build a PMT. I get it from Hamamatsu. But the value addition and the ability to make an instrument that nobody else has really is in putting the sort of components together, designing the whole optics, making your microscope and putting it to. The AFM head was purchased because I had it from long time ago, and I just ripped apart from the existing AFM, put it on, and like this.
Yeah. Heads off.
But there is an AFM builder in India, and he was in Bangalore, Shilp Sciences. And I'm sad to see that he didn't make much headway. But we need to get these people together and have a platform where everybody has like 10% of the ability to make the whole instrument. But if we can have this platform together, come on in, we'll give you a platform, we'll give you other people who can do the other parts. I think we need to do that and start making real instruments which really sell and actually can be marketed.
Yeah. Thank you, Sudipto. I think we are running out of time. We have time for about 15 minutes for a coffee break, and we come here to the next session. Thanks again.
patients who come in from all over the country. So even in terms of ethnic diversities, we have people coming from different parts of the country representing different backgrounds, and therefore a very, very good melting pot of, of Indian ethnicities. And of course, we are an NABH accredited hospital. I know I'm standing in the Indian Institute of Science, which is now going to build a hospital of its own. It's taken us many years of very, very hard work to be perhaps the only institute of national importance in the country in the public space which is accredited by the NABH and is re-accredited recently. So we have 3 broad divisions, and that is what is very exciting about NIMHANS. We have a basic sciences division, which you will see there's a lot of work both in the laboratory as well as on the bench, but very often looks at translational impact of many of these disciplines in terms of trying to understand patients. We do have a central animal research facility, and we have the biological research center where many of the labs of colleagues who work in these departments are concerned. But we also have always been encouraging clinician scientists. So there are neurologists, there are psychiatrists, there are neurosurgeons who also work, for example, with animal models, with the departments of biophysics, neurophysiology, and so on. In neurophysiology, I just wanted to mention that we have a Center for Consciousness Studies, again, which is trying to look at the very, very, the clinical aspects of consciousness or, deep coma to understanding, the concepts of philosophy and enlightenment and so on. Similarly, we have the Department of Biophysics, which does a lot of the work that you were talking about initially, proteomics, cellular mechanisms, crystallography, and so on. We have a Department of Psychopharmacology, which looks at drug metabolism and measurement of drug levels. Of course, we have the Department of Human Genetics and the Department of Neurovirology, which particularly during COVID took a lot of initiative. So, some examples of biomarkers that we would be interested in. Take a typical example of cancer biomarkers. We don't do cancer biomarkers, but it's very, very important that we've seen that cancer biomarkers can be very important in prognosticating conditions like ovarian cancer, breast cancer, and so on. So we at NIMHANS, the colleagues are looking at brain tumors and possible markers used in, for example, glioblastoma and other tumors. So they're looking at promoter methylation areas, chromosomal translocations, various other kinds of mutations, particularly in certain tumors like astrocytomas, oligodendrogliomas, and so on. So therefore, looking at markers becomes a very, very important area to be able to offer prognostication. Similarly, a lot of the high throughput omics as well as DNA sequencing approaches are used in diagnostics, and they are very useful in neurological disorders, in neuromuscular disorders, neurodevelopmental disorders, something that we are seeing much, much more of, in the child and adolescent psychiatry as well as in the pediatric neurology and mitochondrial disorders. And of course, we do whole genome analysis, we do sequencing, we do clinical exome analysis, mutational analysis, and mitochondrial DNA analysis to address some of these disorders. A whole range of omics are things that colleagues do, and that's particularly useful in infections, in epilepsy, in rabies, in Guillain-Barré syndrome, brain tumors, and endocrinal diseases as well. And we are looking at strengthening these proteomic facilities so that they can be much greater application in terms of training and service in the days to come. We have a good department of genetics. We have a section which does a lot of molecular genetics, and this certainly will give us a much better idea about the genetic constitution of various ethnicities, better understanding of the genetic origins of various complex disorders, and of course, developing disease-specific gene panels for diagnostic testing, the early and accurate diagnosis. In fact, I was just discussing with my colleague who works in dementia that perhaps the way we are going is really, particularly for Alzheimer's, to try and see if you can make a diagnostic test so that people know what kind of prognosis is likely and what kind of disorders you might actually exclude. And we do know that the advantages can mean less invasive procedures, which from a patient point of view is extremely useful. And of course, certain diagnostic dilemmas. I think it's easier said than done, because we do know sometimes that one particular disease overlaps. For example, Alzheimer's might overlap with vascular causes for dementias, and that might pose more questions than answers. However, when you look at personalized treatment, perhaps we're looking at more acute prognostication and therapeutics as far as disorders are concerned. Estimation of risk, particularly in tumors, even perhaps in psychotic disorders, looking at the risks of relapse in some patients, and some patients having more, single episodes. What is the reason why that happens? Maybe we can do an estimation of that. Prenatal diagnosis, certainly extremely important when the disorders are genetically transmitted. And when you look at targeted molecular therapeutics, again, the possibility of using genomics, and of course epigenetics, which is really the buzzwords in the last couple of decades, where in psychiatric disorders, to look at addiction, for example, I think there was some discussion about addiction earlier on, and to really predict why certain people relapse, even if the person stops drinking, for example, what kind of epigenetic changes take a long time to recover, might be very useful in following up addiction and psychosis. Similarly, epigenetics can be very useful in understanding the effect of stress on animal models as well as on human beings, drug exposure and its effects. Postpartum depression is another area where colleagues are looking at what might be the impact of the environment of stress to the fetus and how it might affect the subsequent development of the fetus. In Alzheimer's and Parkinson's disease, definitely epigenetic factors are very, very important to look at, as they are in neurodevelopmental disorders like autism. So, the other thing is to look at inflammatory hypothesis. Inflammatory hypothesis and the gut-brain axis are now very, very exciting areas that people are looking at, and therefore seeing how neuroinflammatory processes activate microglia, the astrocytes and the neurons, and then when there are toxic mediators that are released, how that chronic kind of neuroinflammation might explain the pathogenesis of many of the neurodegenerative disorders is something that's very exciting. And of course, looking at HIPSC's stem cells, which I'm sure there's going to be a lot of discussion about. Colleagues have developed stem cells for bipolar mood disorder to look at the effect of lithium on the cells in patients with bipolar mood disorder, similarly in movement disorders and so on. So very, very exciting times in terms of looking at some of the impact of some of these disorders. And when you look at the impact of immunological research on the disease development and the progression, for example, a typical example is antibodies, which has led to the classification of patients with myasthenia gravis depending on the presence of these antibodies. Similarly, autoimmune encephalitis and paraneoplastic conditions, which have been associated with, again, with specific antibodies, development of monoclonal antibodies against disease-specific antigens in a number of conditions. We do know, for example, in Alzheimer's disease, there is a great interest in introducing monoclonal antibodies to arrest the progression of the disease. And of course, the widespread use of immunotherapeutic agents, to augment chemotherapy, particularly in cancers. Another very important area that we've been looking at is screening for inborn errors of metabolism. So colleagues for the last almost 20 years have developed assays to look at inborn errors of amino acid metabolism, fatty acid oxidation, organic acidemias. There are several analytes that they look at. And what they have been able to do is do a dry spot, which can be sent on a postcard to NIMHANS for analysis for detection. And this is so important because just eliminating something in the diet, adding something in the diet can actually get rid of a whole host of neurological, cognitive and developmental problems. And therefore, this is an extremely important area where newborn screening is very, very critical. And this certainly has been very relevant both regionally as well as nationally and internationally. Then moving on to the neuromuscular laboratory, we get a lot of children and adults with congenital neuromuscular disorders, and therefore we are able to, right from immunodiagnosis, molecular diagnosis, enzyme assays, as well as, we're able to look at advanced neuropathies and neuromuscular disorders using the application of all of these techniques. We also have developed a method now of assaying for heavy metals, including lead, and we have the ICP-MS recently. And that helps us to understand particularly the role of environmental toxins, both on cellular as well as clinical manifestations of disease. I move on next to the behavioral sciences, where psychiatry, child psychiatry, clinical psychology, psychiatric social work, nursing, integrative medicine, which looks at yoga and Ayurveda, at least at NIMHANS, and of course disaster management. We've been doing a lot of work on suicide prevention, suicide follow-up. We have a very unique family psychiatry ward where we admit patients with their family members to not only understand the manifestation of disease, but also to help them. And we have a department of psychosocial care and disaster management, which has been doing a lot of training. But again, in terms of understanding the biological implications of disaster, possibly the epigenetic, if we haven't progressed enough, I believe, in that area, and that's something that's very exciting. So when you look at this particular article by Patel et al., talks about how mental health in different aspects of the life course, how people might be at risk, because let's say right from pregnancy to nutrition to inadequate stimulation to the environment and familial risk can affect people right through their entire lifespan, and of course what kind of causes poor mental health conditions. So you really using a lifespan approach, a developmental approach, and understanding what are mitigating factors, what are upstream factors to produce disorders which cause downstream effects. It's a very comprehensive way of understanding this particular problem, and therefore one looks at neurodevelopmental disorders, adolescent disorders, adult disorders, and disorders of the elderly along this particular mental health continuum. And understanding the biology and understanding the interaction of the environment with the individual becomes very important for this kind of understanding. So one of the landmark projects, of course, has been the Telemanas. All of you know that throughout the country, one can call 14416 to actually get help in about 22 different languages. Why am I mentioning Telemanas to a group of scientists here? Because the application of artificial intelligence to prediction in suicide, for example, to prediction in relapses in psychosis, for example, are very, very important and exciting areas of research. So with huge amounts of call data, the likelihood of picking up these kind of risk factors is very high, and that's what makes these kind of arrangements very exciting also for research given the current scenario. Similarly, we have the Department of Integrative Medicine at NIMHANS, which looks at trying to look at not having isolated siloed interventions for people, but actually providing integrative approaches and studying the way the integrative approaches actually work, whether it's in terms of electrophysiological changes, imaging changes, genetic, the epigenetic changes. A lot of that is being developed, and also to understand from an ethnopharmacological perspective how Ayurvedic drugs help and what kind of side effects they may have. So really looking at all of this is something that the Department of Integrative Medicine does. In terms of interventions, we've been very interested in neuromodulation research, and I'll just talk about it in a bit. We've been looking at neurosurgery for obsessive compulsive disorder, telemedicine, something I mentioned, and there's a large study called the Enigma OCD study, as well as the bipolar study, which is trying to look at patients from all over the country, again with different ethnic backgrounds, trying to understand from a multidisciplinary perspective what poses them to risk to develop these disorders and recovery from these disorders. I mentioned neuromodulation. So repetitive transcranial magnetic stimulation is something that colleagues are looking at in a series of psychiatric disorders, from depression to addiction, as well as from movement disorders, stroke, and so on, in a wide variety of areas. Similarly, transcranial direct magnetic stimulation is also being looked at to see what kind of impact it can have, for example, on neuroplasticity. And the fact that these, in addition to electroconvulsive therapy, which is still very commonly used, to see what kind of benefits and what kind of side effects may be occurring as a result of this kind of neuromodulation. We have a very large Welcome DBT project looking at neuromodulation at NIMHANS. And Next, I'd like to go to some of the collaborations, large collaborations we've had. This is something called the CVEDA, and Sona was just mentioning that there's a lot of data which has already been generated in terms of looking at young people at risk for developing addiction. These are the children or first-degree relatives of people who already developed addiction, to see what kind of maturation of their brains occurs, what kind of electrophysiological changes occur, and of course looking at the genetic aspects of it, and seeing what determines the conversion of non-use to addiction, and can we predict people who are likely to develop this. This has also resulted in a brain atlas of how brains mature at different ages, and that has been a very exciting contribution. Similarly, we have the Center for Brain and Mind, and this became possible initially with the DBT funding and subsequently with the Rohini Nilekani Philanthropy funding with the NCBS, where we're looking at a variety of conditions, cross-cutting conditions, bipolar disorders, schizophrenia, OCD, addictions, dementia, as well as healthy controls, looking at both individuals at risks and people who do not have a family history, and looking not just at their clinical aspects in terms of temperament, in terms of their disease manifestation, but also looking at genetic vulnerabilities, environmental risks, doing detailed neuropsychological assessment, structural MRIs, functional MRIs, other spectroscopic studies, electrophysiological studies, and eye tracking, and looking at the commonalities as well as the differences across these disorders. So once again, looking at the brain and mind in a kind of congruent manner and seeing why certain people develop certain symptoms and disorders and others don't is really the most exciting question before all of us. This has also translated into a study called Param, where we are looking across a variety of mental as well as neurological disorders, trying to see what the genome contributes, what the exposome contributes, and the inflammasome as well, considering the inflammatory explanations for disease conditions. We're also looking at a variety of wearables. We're working with colleagues in the United States to see how wearables can also influence the way you can monitor patient symptoms and predict relapse. We do therapeutic drug monitoring for a variety of antipsychotic medications. We've standardized those processes. We test for drugs of abuse. We are the World Health Organization testing agency for tobacco-related products as well. And we have a large number of cohorts. We also work with the Center for Brain and Mind in terms of developing some of these cohorts for perinatal care, for addiction, for psychiatric disorders, and now for neurological disorders as well. Recently, we've been able to digitize about 37,000 patient records from 1850s to 1974. And we, of course, have a hospital information management system. So there should be a huge amount of data that is available for analysis in the days to come. Last part of my presentation, I talk about the neurosciences, particularly neurology and neurosurgery, and the supportive departments that we have. There's some very exciting work in neurology on dementias, particularly on cognitive screening, and of course providing multidisciplinary care. Movement disorders, again, a very, very huge amount of work has been done in terms of a whole lot of array of both diagnostic as well as therapeutic interventions. Epilepsy, stroke, we have part of a stroke registry, and of course epilepsy surgeries. We're looking at developing pediatric neurology services, so neurodevelopmental disorders again becomes very, very important. We are part of global neuro coalitions and as for neuroinfections as well. And CUBI is a very interesting public health model of neurology that colleagues have started to take out diagnostics and screening into the community. And this again is a very exciting area which has now become national. In neurosurgery, traumatic brain injuries, neuro-oncologies, use of robotics, microvascular surgery, movement disorder surgery, disorders of the spine, etc. We've established a neurosurgical skills lab, and which is again very, very interesting for hands-on training in neurosurgery. Similarly, neuroanesthesia and neuroimaging interventional radiology, huge opportunities there for research that are available, particularly brain imaging and mapping, both structural and functional. In terms of academic capacity, we do a lot of postgraduate training, particularly in terms of research. We have a fair number of research projects and outputs as well. And there have been some innovations. This is the part where I'm not very too I believe we have a long way to go in terms of patents, in terms of developing incubation centers, in terms of having many more innovations. I believe we have the capacity to do it, but I think that's where collaboration with other basic science researchers becomes extremely important. So moving forward, what are the opportunities for research and clinicians to work together? Brain imaging, genomics, drug discovery and development, neuroinformatics, and of course looking at brain-computer interface is another very exciting aspect of today's world. And finally, of course, personalized medicine to really determine what kind of combination of environmental and genetic factors make for a certain disease and going forward with that. So we have a lot of national collaborations as well as international collaborations. I don't have time to go into each one of these. They have been very, very useful. And I think as we go on, we will go towards a more developmental approach, trying to understand neurocircuitry and neurotransmitters in much more detail, understanding how psychopathology develops, targeted interventions. We still need better tools and approaches, and I think we're moving towards that. And of course, protection of the brain and mind, detection of an early intervention and restitution of function becomes very important. And for that, we need a multidisciplinary and a multi-technology and a bridge understanding of the brain and mind with, of course, since we're dealing with people, humanism also combined with that. Thank you very much for your patient hearing.
Okay, we'll take a few questions because Dr. Murthy will have to leave after this. For the other speakers, will take the questions at the end. Yes, go ahead.
Thank you, ma'am. Can you explain the crosstalk between brain and mind? How do they
crosstalk? Okay, a typical example is, let us take any neurodegenerative disorder, whether it's Alzheimer's, whether it's Parkinsonism. Inevitably, there are motor symptoms that occur, there are cognitive symptoms that occur, there are emotional symptoms that occur, and there are behavioral symptoms that occur. Generally, the emotional and the behavioral are likely to be studied more by psychiatrists, whereas the movement disorder part of it, are maybe the cognitive is shared between the two. So I think really a approach, a trans-theoretical approach, a transdisciplinary approach is very, very important to understanding why is it that some people, like for example in frontotemporal dementias, present more with behavioral problems, whereas Alzheimer's present earlier with cognitive problems. And these are some things that we still haven't understood. And that really is the crosstalk. Similarly, the crosstalk between psychiatric disorders. Why is it that certain people with a family history of schizophrenia develop schizophrenia and some others develop bipolar mood disorder? What are the commonalities? Maybe in terms of these tools that we have, maybe in terms of the exposome. That's something that we need to understand.
Hello, ma'am. Thank you for the talk. I have been waiting to ask this question whole my life, honestly. I wanted to know, at NIMHANS or India, where does we stand in the migraine diagnosis and research? Because the mechanisms are not well established. There are still hypotheses. And speaking from the first-hand experience, I really want to know where do we stand and how can we contribute to the development of that diagnosis.
So, again, I do not claim any expertise in migraine, so I don't think I would be the appropriate person to answer that question. But you said you all your life have been concerned. There are people, I'm sure 3 times your age, who have also been quite concerned about it. So one does look particularly at vascular phenomena, inflammation. The most, I think the challenging part has been to have a proper drug for the prophylaxis of migraine, which does not produce side effects. So I think we do have some progress in terms of how do you acutely manage migraine, but in terms of migraine prophylaxis, we still don't have an ideal drug which prevents it without producing side effects. So understanding the etiopathogenesis therefore becomes important to try and see whether you can have more specific drugs which act particularly on particular arterial systems of the brain. I think that's going to be a very important challenge.
Just one question, is there any relationship between these neurodegenerative diseases and the profession? Because I have seen some of the neurodegenerative diseases, most of the academicians affect and politicians have these diseases. So is there any relation like that?
So colleagues have tried a lot to look at IQ and the development of disorders, I do not, in my understanding, I do not believe that there are very clear-cut patterns. It is perhaps likely that it becomes much more obvious in people who have very, very high cognitive abilities and reserves when they develop these disorders vis-a-vis others. But we know across the population, and we do know that, in fact, quite the contrary. In fact, the literature probably suggests that nutrition, education, exposure to a lot of information and language proficiency, those are all protective, in fact. The literature suggests quite the opposite.
Dr. Murthy, thank you. That was a very interesting talk. I was wondering, you mentioned a Department of Integrative Medicine. So what are the neurological disorders where you find that integrative medicine is working best? I'm just curious to sort of know about it.
I think one shouldn't jump the gun too much, because they have been used as complementary to, for example, definitely movement disorders, in persons with dementia to some extent. But I think actually discerning, yoga is perhaps a little easier to understand, because yoga can then, can be reduced to the number of sessions you do, the kind of, whether it's a pranayam that you do or an asana that you do perhaps. But some of the other kind of procedures require a certain change in one's lifestyle, complete lifestyle, and measuring that and having the proper metrics to determine what has been your attitudinal change to life, your what do they call, pratiharas, etc., etc. That is very challenging. So I don't believe, there is literature to suggest, for example, that certain kriyas, certain pranayamas seem to help in these disorders, but I wouldn't go to, to make that a solid, completely evidence-based recommendation so far. I mean, I think we just need to understand it better. But I think what my colleagues in NIMHANS are doing is really trying to apply the same methods of studying, other kinds of, what we call Western methods of treatment to these methods, and therefore at least we can get comparators. Right. Now, whether they will have the same thing by disproof, as Western methods of approach, or whether we will have some unique findings is, I think, remains to be seen.
Thank you. Very interesting.
Thank you very much for your wonderful talk. Thanks a lot. Shall I use this one? Thank you. I'll be switching gears now and trying to sort of show one possible way of bridging the gap from the human condition to model systems where we can study the disease using human cells instead of animal models and see if we can get some new insights. This work I'm going to talk about was done in NCBS in Bangalore. I've since moved on to found a new institute in Kolkata, which is focusing entirely on translational neuroscience. The example I'll talk about today is that of Fragile X syndrome. The leading monogenic cause of autism and intellectual disabilities is caused by a mutation in a single gene called the FMR1 gene, results in an abnormally high production of proteins, and it's more prevalent in boys than girls. And there are a range of symptoms listed here, and my past work and the current work I'm going to talk about has focused largely on anxiety and seizure symptoms. Now, Fragile X syndrome and other such disorders have been studied extensively using animal models, mostly preclinical rodent models, and these have focused entirely on the neuronal, synaptic, and molecular basis of the pathophysiology of the disease, and has given us great new insights into identifying new targets that can be drugged. And this is an exciting area of science. However, sadly, these don't translate, these findings eventually when these targets are taken to trial in humans, they don't translate very well, and more often than not, they result in a very prolonged, expensive, and eventually mixed results at best. As a result of which now major pharma companies are pulling out of this area altogether because for them it's not good business. Yet the problem remains. And what we have found over the last several decades, that despite very exciting new findings in neuroscience, such as Fragile X syndrome, these don't translate into therapeutic interventions of the kind that really works in the real world. And Fragile X syndrome, unfortunately, has become a poster child of this. So what we have learned from this process is that humans are bad models for rodents. And we need to now work on model systems that are of human origin, and maybe that will mitigate some of these challenges that we are facing from translating from animal models to humans. So I'm going to give you an example of that, work done by 3 very gifted people in my lab at NCBS who have now moved on. Shreya is now a postdoc in Edinburgh. Rakipal and Bharat Reddy have moved with me to Kolkata. They did the experimental work, and I must acknowledge Rishikesh Narayan's input in the thinking of this project, and at pivotal points he helped me with new ideas of experiments. So I'd like to acknowledge him as well. Now, this work involves fairly standard protocols of generating iPSCs from human fibroblasts that are eventually programmed to become cortical neurons in this case. These are patient-derived cells, and to complement that, we of course now it's standard to have CRISPR gene-edited control lines as well from ESCs. Together they constitute the kind of set of cells one studies in this model. And in this particular study, we had 2 control patient lines, 3 Fragile X lines, and then 1 gene-edited line. I will interchangeably refer to the Fragile X lines as FXS, the disease lines, and the controls all together. They all show the same phenotypes, and so I'm not going to break them up into these subclasses. And then, along with these cortical neurons derived from these patients, we also generated astrocytes, human astrocytes, and they were eventually mixed together to have a co-culture wherein you have both the cortical neurons and the astrocytes together in a system that has some remarkable properties that I'll talk about. And just to give you a glimpse of what these look like, the gene-edited lines, the control line, the 2 patient lines, and these are the co-cultures shown here, and they lack the FMRP, the Fragile X mental retardation protein. Now, all the data I'll show you is often of electrophysiology, because I do not understand anything that has anything to do with molecular biology. So I'll stick to my lane, and what you'll see today is these cortical neurons co-culture with cortical astrocytes, and the recordings I'll show you are entirely from the cortical neurons, although you'll see that the astrocytes turn out to be the stars of this story. So if you now record from these neurons in these co-cultures, you have basically 4 combinations. You have either Fragile X neuron or control neuron, Fragile X astrocyte, or control astrocytes. In a 2x2 grid, you have 4 combinations, and we'll talk about all 4 combinations. And now for some astrology. So the first thing we observed is that if you have a co-culture of healthy control cortical neurons with control astrocytes, the control neurons fire action potentials in the following pattern. Now, action potentials are spikes of voltage spikes that are the currency of communication that Sudipto briefly mentioned about in terms of synaptic transmission. It's the action potential that arrives at the synaptic terminal and that releases the transmitters that Sudipto was talking about. So this is the currency of communication between neurons, and what we see in these control neurons with control astrocyte condition is that the cells fire bursts of prolonged action potentials, but then between the bursts, there are long intervals, time intervals. This is the healthy firing pattern. Now here is a cell that's also genetically a control healthy cortical neuron, but it's firing very differently and an abnormal pattern compared to this. It's firing bursts of action potentials which are brief, and there are too many of them. Okay? Here you had a few prolonged bursts. Here you have too many bursts which are all individually very short. But this is a control neuron. Why is it firing like this? It's firing because it's in the company of a Fragile X astrocyte. So a control neuron, just because it's in the neighborhood filled with Fragile X astrocytes, it now starts firing completely differently. If you now take a Fragile X neuron with a Fragile X astrocyte, you also see this aberrant firing pattern where there are too many bursts and individual bursts are too short. And finally, the interesting part of it is you now have a Fragile X neuron in the company of a healthy astrocyte, and although this is a Fragile X neuron, it's firing like a normal neuron just because it's in the company of a healthy astrocyte. So this is quite remarkable that despite being genetically a Fragile X neuron, it's firing normally, which means just adding the healthy astrocyte changes its behavior back to normal. So you can do a correction by just using healthy astrocytes. So what it means is that if you have control neurons with control astrocytes or control Fragile X neurons with Fragile X astrocytes, you see these two aberrant firing patterns. However, if you have a Fragile X neuron with control astrocytes, they fire just like these. And conversely, if you have the opposite combination, these fire like this. So it's the genotype of the astrocyte that determines the electrophysiological firing of the cortical neuron, right? It's not the genotype of the neuron that determines the electrophysiological phenotype of the neuron. So we quantify this, of course, the two parameters, the duration of the burst and the interburst interval. How sparse are these bursts? Those are the two parameters, fairly simple. And we then plot them. You can see that the control neuron with control astrocyte has fewer bursts, and that changes when you add the Fragile X astrocyte, and conversely, the duration can also be modulated. Duration and numbers can both be modulated. And each case, this bar's property is determined by the color of the astrocyte. You can do the converse. So if you go this, there's no difference between these two, despite the fact that they're both, they're both Fragile X neurons, but it can convert based on whether they're in the company of the astrocyte. And you can do the same the other way around. Fewer bursts, longer duration can happen in this case as well. So essentially, there's something coming out of the astrocytes that is able to regulate how the human cortical neurons will fire. Now, to probe the underlying electrophysiological mechanisms, and because these are electrophysiological phenotypes, it gives us a huge handle on this, because the underlying ionic basis of these firing patterns are well known from the literature. So we focused entirely on what kind of potential ionic channels could underlie such firing patterns. And based on the previous literature, we honed in on something called the persistent sodium current that has been shown in mouse models of Fragile X to regulate rhythmic burst firing patterns. And we thought we should go after this and see what happens. To isolate this particular persistent sodium current, one has to hold the cells at a negative potential, bring it down, and then ramp it up as shown here, 20 millivolts per time, and then go back all the way up here and bring it back. So this ramp is a way of revealing the persistent sodium current. So what you do is you first inject this depolarizing ramp in the neuron and record. Then you use TTX to block out the regular sodium current in the same neurons. You hold on to that neuron and do the ramp again now after TTX and see what happens. And then you subtract this trace from that trace, and what is left is the persistent sodium current trace. So you'll see examples of this. So this is now the control Fragile X combination, and you can see that the control neurons show this tail current, and with Fragile X that is completely missing, the flat red line. So this is the difference. This is the persistent sodium current, okay? In the Fragile X condition, that's completely missing, goes missing. In the control condition, you have this tail current. And you can average these recordings, and you can see there's a huge difference in the current density. In the Fragile X condition, it's completely abolished in the Fragile X condition. And one can do this with the cross combination of control neuron, Fragile X astrocyte, and vice versa. You can see the same phenotype. So this current clearly is getting impaired in the Fragile X condition in all of the 4 combinations that we have looked at. So far what we have is normal firing, aberrant firing, and the persistent sodium current is normal here, and it's impaired in the Fragile X condition. So the question, of course, is that we have isolated two different phenotypes. Are they linked to each other? So one way one can do this is to see if we can somehow reverse this impairment of the persistent sodium current by enhancing it pharmacologically, and would that then rescue the firing pattern phenotype that we are seeing? So it's a pharmacological experiment. So there's a drug called veratridine which does exactly that. It opens up the persistent sodium current channel, and so we use that because it's been used in the past in mice. So here now is an experiment where you just add veratridine to the bath, and you see that there's an impaired persistent sodium current, and that's rescued back to higher levels as you see in normal cells. And you can see that as well in this other cross combination, the same thing. So veratridine does rescue the impaired persistent sodium current in the human neurons, and this is the first time that anybody showed this. So now the question, of course, is, okay, veratridine is expected to do this, and it is doing it in human neurons, that's fine, but does it rescue the actual phenotype? So here again, we do a within cell, the same cell comparison. You first establish the abnormal burst firing in the Fragile X condition, then you wash in veratridine for 10 minutes, and you wash it out, and sure enough, you begin to see the normal burst firing pattern again within the same cell. And these are then quantified here, and I won't bore you with the details. And you can do it in the opposite combination as well, control neuron Fragile X astrocyte, and you can get the same rescue back. So this then tells you that if you use a drug that can reverse the impaired persistent sodium channel current, you do rescue the phenotype, okay? So we have a target now. So the summary so far is by enhancing the persistent sodium current pharmacologically, we can restore the firing patterns. Then came an interesting bifurcation point where I thought of doing an experiment that was rather unlikely. We wondered if you really need the astrocytes in the co-culture in contact with the cortical neurons. What if we just take them out of the circuit altogether? What happens then? So here now what we're doing is we're growing the astrocytes separately, we're growing the neurons separately, and at some point, instead of adding the astrocytes to make the co-culture, we're just adding the conditioned medium from the astrocytes into this and go on with the same experiments. So now the astrocytes are physically replaced by whatever they're secreting as a soup, and put that into the neurons and see if that's enough. This is what I call the Russum experiment. And so the astrocytic Russum is good enough for these neurons to grow on their own. That was confirmed. And then came the big one. You have a control neuron immersed in Fragile X astrocytic conditioned medium. So the astrocyte's missing, just the soup is there, and it can make this healthy neuron fire like a Fragile X neuron as shown here. You can do the converse, which is the therapeutic intervention angle. You can take a Fragile X neuron, immerse it in healthy controlled astrocytic medium, and it starts firing normally. And you can see the same transitions in burst duration and burst number that I had shown you earlier. So this is doing the exact job that you'd want you to do in terms of correction. So what we have now is these two conditions are the boring ones. They do what you expect. But the interesting one is that with Fragile X, control neurons, Fragile X astrocytic medium, they convert, and most importantly, Fragile X neurons, just by washing them onto, you wash in the control astrocytic medium, and it fixes it. So then the question comes, what is there in the astrocytic Russum that's really fixing this? Now this is of course a big question, because this Russum, like the real Russum, has a lot of ingredients, and going through them systematically is quite complicated. Some of them are necessary for the growth of the neurons. So again, we sort of, it's a needle in a haystack problem, and we again resorted to an electrophysiological sort of angle. Our argument was fairly simple. Whatever this candidate is being secreted in the Russum from the astrocyte should be of astrocytic origin. It should be able to recapitulate whatever veratridine did. It should do the same thing in terms of correction. And it should have some known properties for modulating neuronal firing patterns. So it turns out, and this is where Rishi's help came in, there's a paper published with a mouse model system where similar properties in a different context were shown to have, where they identified S100 beta which is of astrocytic origin, to do some of the things that we are hoping it would do. The actual effect in the mouse model was opposite to what we were hoping, but we still tried it to see if it works. So again now, this is the question now. Will it act on the persistent sodium current? And if so, will it correct the abnormal firing pattern? So the same kind of experiments. Now, instead of washing in veratridine, you wash in S100 beta onto a co-culture of Fragile X neurons with Fragile X astrocyte. And indeed, the impaired persistent sodium current shown here in the flat red line is rescued. You get the normal current back. This is the average of those findings. The cross combination, you get the same thing as well. So S100 beta is doing the job in terms of reversing the impairment of the persistent sodium current. So that's the first step. Then the question, of course, is would it also rescue the firing pattern? Because we have found this correlation with veratridine earlier. Would S100 beta do the same thing? So get baseline recordings, wash in S100 beta, and then see what happens in the same neuron. And so here is an abnormal firing pattern, wash in S100 beta, you start getting more prolonged bursts. And if you do the other way around with control neuron Fragile X astrocyte, you get the same, you rescue. This S100 beta alone is able to restore the normal burst firing pattern in the Fragile X cortical neuron condition. So S100 beta is indeed doing the job, and it is of astrocytic origin. So in summary then, what I've shown you is that in the human Fragile X condition, for the first time, we're able to show that there's a cell non-autonomous effect in Fragile X cortical neurons, in the sense that it's the genotype of the astrocyte that determines how the cortical neuron will fire, whether it will fire abnormally or normally. Further, we showed that you can replace the astrocytes with their conditioned medium, and you can do the same rescue. And then we went on to identify one particular molecule secreted from the astrocytes, S100 beta, does the same job. Okay? So one of the things that I'd like to point out is that we had done similar experiments earlier in an earlier study where we had used human cortical neurons co-cultured with mouse astrocytes, control mouse astrocytes. We got the same firing patterns, but although those astrocytes, the mouse astrocytes, were control healthy astrocytes, they were unable to rescue the abnormal firing in the Fragile X cortical neurons, which means it's only the human astrocytes that's able to do this rescue, not the mouse astrocytes. Further underscoring the importance of using model systems of human origin. Okay? So sort of going back to the bigger picture then, much of the Fragile X work for the first 20 years, our work included, focused entirely on synaptic plasticity, aberrations in synaptic plasticity as the key underlying cause for Fragile X syndrome. And these were in rodent models. More recently, groups of people switched to intrinsic plasticity and network activity in mouse systems to show they do play a role as well. What we have introduced now is that we've gone to a co-culture network system that includes both cortical neurons and cortical astrocytes, and shown that not everything is lying within the cortical neuron. There are ways of doing this in terms of cell non-autonomous effect and giving us these astrocytes as a new potential target for therapeutic intervention. So the game changes now. We can look for new ways of reversing defects in the neurons by acting on the astrocytes. So I'd like to thank the folks who've done the work, our collaborators at Edinburgh, funding from the Department of Biotechnology, and Simons Foundation. Thank you very much. Yeah, questions?
So the question is the therapeutic intervention. At what stage do you think this will be effective? I mean, you've given us enough evidence to show it works.
Right.
But considering it's already a neurodevelopmental defect, so
That's
what's
right. Yeah. So that brings up a more fundamental question, which of course you are much more aware of this literature. In the mouse models, the huge deficit, and we're guilty of this as well, is that we look at adult phenotypes in a neurodevelopmental disorder, and very little has been done in terms of the progression.
Sure.
Right? So I have taken this back to the rat model now, trying to map out the progression. But in this case, what we see is that these neurons are not really mature neurons, like truth be told. They're very young neurons. But within that, we find that you need at least 8 weeks in vitro for these neurons to mature enough to show these firing patterns. And if you go too far, the astrocytes are so overwhelming that the whole thing lifts off. So you have a very narrow window. So I think the only way to answer your question is to really map it from early on, except we have a limitation that the electrophysiological phenotype is only showing up that 8 to 10 week window, which limits us. So I think we'll have to go back to the drawing board and come up with other phenotypes, more molecular in nature, that can circumvent this problem. But it's a key question that you asked, yes. And we don't have a clean answer to it yet. Yes.
Hi, Shona. Wonderful work. I was wondering, the S100 beta is a calcium sensing protein.
Right.
And, do you suspect that it's directly activating the sodium channels, or is there some other pathway that it follows?
Thank you for asking that question. It is something that Professor Balram pointed out very early, 5 years ago. And so we have done experiments where we have actually played with the concentration of calcium in the medium, and we can switch the firing. So it's clearly S100 beta chelating calcium to some level, optimal. And that must then go through the BK channel or something to modulate. How persistent sodium current channels are linked to that is a big mystery. And it's an intensely researched area. It's not very clear. There are different hypotheses. But for us, we need to first figure out S100 beta's action there. And why didn't the mouse one work? And there seems to be differences in a few in the sequence of S100 beta in that calcium binding domain in mouse versus humans. And that's something we're starting to look at this summer. Yeah.
So is the concentration of S100 beta different between Fragile X and control? Is
yes,
that what is
I
drawing
had that slide. I took it out in the interest of time. It is lower in the Fragile X astrocytic condition medium. We also did a couple of other studies. We also tried to puff on S100 beta onto the cell because you just don't know what concentration is reaching it when it's in the medium. But those are difficult experiments because they wash away very quickly. So even with the puffing, we could rescue the phenotype for a little bit, but there might be better ways of doing it in terms of actually genetically manipulating S100 beta in the astrocytes, which might be a more stable way of doing it. Yeah. But there is a lowering of the concentration in the medium, yes. Yes. Professor Sigler? Yeah.
Sir, it's
yeah, okay, go ahead. Go ahead.
It's an interesting talk, but I have a small doubt. So, in an overall picture, when healthy astrocytes media is taken and it is injected to the neurons, it regains its firing ability. So is it possible that if we filter out the CSF of many of the proteins which are immunogenic and then inject it to a person who is affected, so will those small molecules help regain the metabolic dysregulation which caused the disease?
Yeah, so I think S1 inhibitor was picked entirely because of my bias towards electrophysiology. One has to go systematically and screen for what other potential molecules could be involved, and I'm sure there are. IL-6 is one that we're looking at, and so that has to be done more systematically. We'll just take one last question from Professor.
Yeah, nice talk. There are two questions. One, you are probably aware that astrocytes, they do exocytosis as well.
Yes.
I mean, this has been shown by capacitance measurements. So do you think this is secreted by the astrocytes? I mean, actively?
I think exosomes would be the way to. So we have to look at the. Yeah, we have to analyze that. We haven't done that yet.
The second question, I mean, you are aware that, when you do a neuron astrocyte culture, the astrocytes proliferate like hell and beyond a certain point. So do you have a cutoff time? Or
10 weeks. 8 weeks, enough to keep it stable, get the firing going. By 10 weeks, they overwhelm and take off and lift off. And that's it. So that's the window.
Thank you.
Right. Thank you. We'll move on to the next speaker. Thank you. We'll do it at the end because we just want to keep the time for now. Yeah, go ahead. So the next speaker is Dr. Nitin Chauhan, and he's at TIFR Mumbai, He did his PhD in Würzburg and then his postdoc at UPenn, and he works on the fly system, and he'll talk about sleep in flies.
One more question, sir. See, S100B proteins, interaction with calcium
yes.
is unlikely to be involved here, because generally S100 proteins will act in concert with other molecules, such as NX and beta, or even TLR4. So did you probe the role of other receptors?
No, we don't. We don't, and I'm the first person to acknowledge that there are other cofactors we have to look at. The problem is with electrophysiologists, we are stuck with certain restrictions on that, and there are certain experiments we cannot do yet, but those are on the list.
Thank you so much for the introduction and this opportunity to invite me to present our work in this meeting. So I'm going to talk about sleep, a behavior that I don't need to introduce. We all engage in daily, and it is required for a bunch of different physiological and cognitive functions. But what I would like to argue today is that its functions are not rigid, but incredibly flexible. And it's this adaptability that can give organisms tremendous flexibility to survive in different environmental conditions. So before going into that, do we even get 7 to 9 hours of recommended sleep every day? So these are the bunch of studies. I don't know how much you can look at it. But essentially, these are done across different countries with the help of activity monitors to figure out sleep patterns in different populations. And it was observed that in countries that are typically rank higher on the happiness index, there the population tend to get 7 hours of sleep every night. But if we look at India specifically, that number drops down to 6.4. Another interesting aspect that was discovered with these data sets is that the time to go to bed and wake up strongly correlates with the amount of sleep that you get. So if you go to bed early and wake up early, those are the same countries which were getting 7 hours of sleep. The only anomaly is Russians. They go to bed late, wake up late, but still get a lot of sleep. So other than them, most of the other countries are following these trends. Now, humans are not unique to get sleep. In fact, organisms across the animal kingdom show some sort of sleep-like state, going as low as invertebrates, which can sleep for 2.6 hours in worms, to ants sleeping for 5 to 9 hours, to some species of bats that can sleep for 20 hours in a day. So these are defined on various criteria, but what is clear is a sleep-like state is visible across the kingdom. But still, the behavior remains enigmatic because we still do not completely understand what exactly it is doing. And we have some clues. If we don't sleep, what will happen? So most of the sleep manipulation studies suggest that if we don't sleep properly, then there will be impairment in the bodily functions, including cardiovascular health, immune function, metabolism, and also have effects on brain functions, including learning and memory and social behavior. Even at a cellular level, there are various studies showing some or the other defect of not sleeping properly. So I will be concentrating on learning and memory. We largely try to understand how this link between sleep and learning and memory is established. And the link is in fact reported quite almost 2,000 years back by a Roman educator named Marcus Quintilinus. So he observed that the strength of memory, which seemed weak, was suddenly strengthened the next day on tasks that were not easily recalled on the spot. So this is not directly implicating the role of sleep, but in fact some process that is happening during the night which might be relevant for this type of learning and memory. But the experimental evidence for the role of sleep in learning and memory was only obtained like 100 years back. In this set of experiments, graduate students were given certain nonsense syllables to remember, and then were either allowed to sleep or kept awake. The group that was allowed to sleep was better at recalling those nonsense syllables, but the group that was kept awake was easily forgetting those syllables. So this gave first evidence that sleep might be playing some sort of role in either the consolidation of the memory or the recall of the memory the next day. So similar studies in other model systems further strengthen this idea that sleep and memory consolidation processes are linked. And we study these processes in the humble fruit fly, a genetically powerful model system, and essentially have contributed immensely to our understanding of various behavioral neurogenetics. So first I would like to convince you that these tiny flies are capable of learning and sleeping, and how actually we go about measuring those parameters. So for learning, these apparatus were developed by Seymour Benzer at Caltech in early 70s. And these are countercurrent devices which take advantage of flies' ability to move towards light. So they are really attracted to light, so they introduce flies here, and there's a light at the top, so these flies are going towards the light. At the same time, there's an electric grid that is placed in some of these tubes, and there's a specific odor, a specific smell, which is associated with each, a different smell with each tube. So the experiment is quite simple. You introduce the flies at the bottom, and when they go up, the odor, in this case odor A, will be presented at the same time the electric grid is giving them shocks. So they will form an association between the two. And then there's a second odor where the electric grid is no longer giving them shock. So they will form different memories for different odors. So when they tested their memories, they found that the odor that was associated with electric shock, they avoided that odor significantly compared to the control odors, giving the first evidence that flies can remember this association between an odor and a punishment. Now, how about sleep? So we cannot put electrodes on, we can actually, but recording EEG is not feasible in fly system. So instead of an electrophysiological definition of sleep, we rely on a behavioral definition. So we have defined certain criteria that are essential for sleep, including periods of immobility, a specific posture, an increase in arousal threshold, and a homeostatic regulatory mechanism. I'll come to these in a moment. So the way we do it is we introduce flies in a small tube, and there's an infrared beam running through the center. So whenever fly is moving, these beams will break, and that will be counted as a measure of activity. And if flies are inactive for a period of time, then we take that measure as sleep. So as you can see here, flies typically sleep diurnal. They sleep throughout the night and also obtain some siesta-like sleep during the middle of the day. Now, what about the other criteria? So they do change their posture while they are sleeping. They typically move towards the food and relax. Their arousal thresholds also increase. So here we are using some vibratory devices which will give different strength of stimulus, and when they are sleeping, the strength of that stimulus is higher. So it takes much more intense shaking to wake them up, indicating that they are not awake but in some sleep-like state. And finally, the homeostatic rebound is based on the idea that if you keep them up all night, the tendency to fall asleep would be higher the next day, a behavior that we all experienced at some point. So here in flies also, if we deprive them of sleep with the help of some mechanical shaker, the next day they sleep much longer, which indicate that there's an homeostatic rebound resulting from our manipulation. So like other model systems, sleep is incredibly important for various behaviors in flies. For infection and injury. If you infect flies with a pathogen or you injure them, you see there's an increase in sleep in those flies. And if you don't allow them to sleep, then their ability to recover from the infection is significantly deteriorated. If you don't allow the fly to sleep at all, then they die much faster compared to the controls. In addition, the cognition also changes. Their attention span is lower compared to controls, and their ability to form memories also changes based on how much sleep that they are obtaining. Now, coming to this idea about sleep flexibility, all these functions that I mentioned, of course, sleep is important for them, but sleep as a behavior itself is highly influenced by environmental changes. So if you are keeping animals starved, their ability to obtain sleep decreases, presumably in search for food, as shown here. If you keep the animals, in this case flies, isolated, an experience that some of us may have experienced during COVID, again, the sleep is significantly lower, and temperature changes also changes the amount of sleep and even architecture of sleep. So all these environmental changes are having an influence on sleep, but then the question arises, how would that change the ability of sleep to cater to all those different functions that I talked about? And that's what essentially we try to study in our lab, how wakefulness would affect those sleep-dependent functions, specifically learning and memory in these model systems. So to study that, we use appetitive conditioning. So I talked about electric shock and odor combination, but instead of electric shock, we use reward, like sugar. So these flies are given sugar with an odor, and then given another odor, this time without sugar. Now, to create an artificial situation where flies will be unable to sleep, we keep them starved. As I mentioned, they are unable to get enough sleep when they are starved, or they are kept fed. And then we, next day, 24 hours later, we introduce them back into this similar device, but now give both the odors together. So based on if they remember which odor was associated with sucrose, they will move towards that odor more, and based on that we calculate a performance index. A higher the performance index, the better their ability to recall whatever they learned. So what we found is in flies that were kept on food, so completely satiated, if we sleep deprive them during after training, their performance indices dropped significantly, indicating that sleep was necessary for them to form whatever memory that they were forming between odor and reward. In contrast, in the case of starved flies, if we do the same thing, if we sleep deprive now the memory is not affected by sleep deprivation. So even though the training is the same, two different types of memories are formed based on whether they are able to sleep or not, based on feeding conditions here, fed or starved. So not only sleep seems to be dispensable for memory consolidation, but it seems that it is acting negatively on memories in starved flies. So what we observed that these flies were more active after memory consolidation, and if we artificially induce sleep with the help of a sleep-inducing drug, in this case carboxydol, these flies' memory performances dropped. And if we sleep deprive them, we rescued those memory performances again. So not only sleep is dispensable, it seems it's acting negatively if these flies are forming what we call sleep-independent memories. So this was what I just showed you. In fed flies, we saw an increase in sleep and seems to be forming memories that are sleep-dependent. In starved flies, we don't see any change in sleep, but we instead see a change in activity, an increase in activity. And here they are forming sleep-independent or activity-dependent memories. So not only flies, these type of behaviors are also observed in the wild in different animals. Killer whale mothers, when they are typically give birth, they move away from their pods. And while making the return journey, which can expand for 3 to 4 months, these mothers as well as newborns show no signs of sleep, which is strange because that's the period where newborn is learning a lot of new techniques. Garden warblers, which are migratory birds, travel across for months, and during that time they also don't show any signs of sleep. And elephants do the same while searching for food across the African plains. They also show no signs of sleep. Of course, in humans also we have chronic sleep deprivation, insomnia problems, which are exaggerated by our current lifestyles, but a direct effect on physiological and cognitive functions is hard to determine. And I would like to argue that in these cases, a sleep-independent mechanism might be playing a role. So before going forward, I just wanted to talk a little bit about how memories are formed in the fly brain. So this is how a fly brain looks like. When an odor is provided, these antennal lobes, these blue colored structure, first process that information and then transfer it to these higher brain centers called mushroom bodies because they look like mushrooms through projection neurons. So the way memory is established is these are different dopaminergic neurons, PPL1 and PAM. And what they do is they modulate the connections within the mushroom body neurons such that when the odor is presented again, the approach or avoidance pathways are differentially regulated. So that if a reward was presented with an odor, a fly will approach that odor, and if punishment or a shock was associated, then it will move away from it. So what we found was for our sleep-dependent and independent memories, the underlying neural circuitry is completely different. So here, I would not go into the details of this, but what you can appreciate is different set of neurons are required for memories when they are forming sleep-dependent or sleep-independent. Even though, again, I like to emphasize the training is the same. They were both given odor and sucrose, but based on whether food was available, they are forming different types of memories. So here I would like to switch gears and talk a little bit about what we are currently doing. And I briefly talked about temperature, how temperature changes the sleep patterns in different model organisms, and that's also true in flies. Here I'm showing you rodent data, which are nocturnal animals. And what you can see here is during nighttime, there is a decrease in their body temperatures compared to their active periods. And in fact, if the transition from wakefulness to sleep is preceded by a decrease in their body temperatures. And if there is a decoupling between body temperature and sleep-like state, then insomnia-like behavior is observed in these animals. Now, in humans, similar studies through various surveys have concluded that lower temperatures don't have that much of an impact on sleep states, but higher temperatures can result in a significant decline. And that begs the question, what would happen if there is a considerable increase in external weather or even acute temperature increase? An experience that some of us may have experienced, but with increasing global temperatures would become a much more serious issue. So in these cases, the expectation would be some sort of stress response will be activated. In fact, it has been shown that the cortisol levels go up when humans are exposed to a high temperature, even for short periods of time. And we would like to study what would that do to our ability to form memories. Is the function of sleep remaining the same or changing based on these high temperatures? So this was first looked at in C. elegans worms. And what it was observed that if you give them a heat shock, they show an increase in sleep. And if you don't allow them to sleep properly, then their survival is down. So something similar to what we observe with immune stressors, immune challenges. There also, sleep seems to be playing a significant role in recovery, in survival of animals. Now, we have done similar experiments in flies, and we also observe that after a heat shock, there is an increase in their sleep. So first we wanted to look at whether this is also true in starved flies, the ones that are forming sleep-independent memories. And similar to fed flies that show an increase in sleep, our starved flies also showed an increase in sleep after a heat shock. So here they are kept on at 38 degrees Celsius for an hour for heat shock conditions. So next we looked at what would happen to memory consolidation. So flies were trained and then exposed to a heat stress, and then looked at whether that has any effect on their learning and memory. So again, performance indices suggest that in both starved condition and fed condition, just giving them a heat shock resulted in a significant decline in memory consolidation. So in both conditions, even though the sleep is going up, memory consolidation seems to be impacted. Then we sleep deprive and see what happened, and in starved case we were able to rescue that sleep, the memory decline, but in fed case we were unable to do that. So it seems the heat stress is differentially affecting sleep dependent and sleep independent memories, and our current data suggests that dopamine might have a role to play in how these different mechanisms are activated. So I'll quickly talk about what we found with dopamine. So here we are using a genetic construct to, we have introduced a genetic construct in specific dopaminergic neurons in the fly brain. And what this construct will do is whenever a neuron is active, this will generate a luminescence-based signal which can be read by a plate reader. So what we found is after heat shock, these dopaminergic neurons were more active compared to the control condition. And then to further look at their behavior, we used optogenetics to artificially activate these neurons after training. So here we are not giving them any electric shock, heat stress, but in fact just activating them with the help of optogenetics. And what we found is the performance index is declining, indicating that this neuron, this particular dopaminergic neuron might be the one which is getting recruited by the heat stress to change this memory pathway. I will not go into the details of these other aspects that we discovered, but what our current data is currently showing is the way heat stress is recruiting dopaminergic system to then increase the activity of a particular receptor, which is also a receptor for a steroid hormone called ecdysone, something similar to cortisol in mammals. So we are trying to figure out how this connection might be functioning, but at this stage, what we can say is the differential effect of heat stress on sleep-dependent functions versus sleep-independent functions might be down to the differential energy requirements for these two pathways. So what do I mean by that is whenever there is a heat stress or a stress of any sort for that matter, to increase recovery from that stress, a lot of energy is required. And to facilitate that system, what our data is suggesting, the system is taking that energy away from processes like memory consolidation. So the decline in memory performances or the impairment of memory consolidation is essentially to facilitate the recovery from the process. And if we don't allow that recovery to happen, if we artificially make them still learn in those heat stress conditions, then their overall survival is getting affected. So this mechanism is allowing to keep this balance to allow an organism to survive, and sleep seems to be playing a major role in this toggle from memory consolidation or survival from a heat stress like stressor. So this is my lab at TIFR Mumbai. Most of the work that I showed you today is done by a graduate student named Kamakshi, and these are the funding sources. And thank you so much for your time.
Thank you for the great talk. It was really very clear and I really enjoyed a lot. And when you talked about heat stress, I was wondering, and since you were also talking about the environmental effects, I was wondering, like the example in like Scandinavian countries, when in the summer it's always light when they're going to sleep, and in winter, so still if you sleep for 7 hours, and by the way, I have to say that is the 7 the new 8, because we have been hearing 8 hours through since our childhood.
7 to 9.
Okay. But anyway, so is the sleep quality affected depending upon the external, like sun, because temperature is maintained because of air condition, it's just the environmental factor which is different.
So the studies that I showed you, those were Hungarian surveys which were done over 25 years. So yes, modern technology now allows us to maintain our internal room temperatures to an extent which can help us to fall asleep better. But those surveys were started when those technologies were not available. So there we can see that if you decrease the temperature, even take it to negative, it doesn't affect sleep that much. But even a 10 degrees Celsius increase in temperature from 15 to 25 seems to decrease it. And we are talking about temperatures above 40 degrees Celsius.
Sunlight doesn't have any correlation with the quality of sleep then?
I mean, sunlight is essentially giving a circadian signal for them to maintain when to sleep or when to keep
That's
active.
true, but if you take example of Norway, for example, you maybe get sunlight for 2-3 hours, and then in winters, and then in summer you don't get dark when you go to sleep. So that's what I meant actually.
Okay, I mean, it's so whatever I've shown you today, it's largely done with 12-hour cycles. But other researchers have delved into that question to decrease the cycle lengths and see what happens. It drastically changes their behavior, but it doesn't really increase the quantity or quality of sleep. So they become more active, but they then remain active even during the dark phase. So there is a change, but it's not like they are sleeping more just because of that.
Thank you.
One more question and then we'll go to the rest.
I have a question. Is there any difference in the nature or pattern between sleep-dependent memory versus sleep-independent memory?
So with sleep
in terms of long or short-term memory or things like that?
So all these experiments that I showed you are for long-term memories. The sleep pattern, so quality of sleep is much higher for sleep-dependent memories. If you decrease only the quality of sleep, which essentially means fragmenting their sleep, then the memory is affected. For sleep-independent memories, they're completely dispensable. Even if they are not sleeping at all, they will still form that memory.
Okay, we'll move the rest of the questions to the end of the session after Arun's talk. Thank you very much, Nitin. So our final speaker is Professor Arun Shipati from the Center for Neuroscience at IISc. He is also a new fellow of the Academy, and he did his PhD from Johns Hopkins and postdoc from Carnegie Mellon. And there's more to Arun than meets the eye.
Thank you. Okay, so thank you. Not sure if it's audible. Can you hear me? Maybe I should use this. Yeah. Can you hear me? Okay, so thank you. It's an honor to be here, and I look forward to sharing my work with all of you. I'll get right into it. I grew up reading a lot of work by Asimov, and I was fascinated by sci-fi. And these sci-fi books talk about worlds where robots are interacting with all of us. And if you start thinking about why we don't see robots sort of around us today, you'll notice that we're still typing into machines instead of talking to them. We have machines that will create beautiful artwork and write poetry, but they won't tidy up your room and wash your dishes. We also have to scan items in barcodes instead of machines just recognizing things by seeing. And if you think about it, machines are actually failing on exactly the tasks that we're actually finding easy. So the things that we find hard, like multiplying 8-digit numbers or whatever, taking the square root of 2, those are the things where machines are doing really well. But the things that we actually do really easily are exactly the ones that that machines are unable to do. And one prime example of the fact that machines are unable to do the simplest of tasks is things like this, which all of you see on websites. Anytime you're doing an important transaction on the internet, you have to cross this barrier. And this barrier is there because to be a human being on the internet, you just need to recognize distorted letters. You don't have to believe in democracy or have good feelings for your fellow men. But machines can't do this task. And this is kind of amazing because how is it that machines are actually, how is it that we are not able to make machines do a task like this? And this is sort of the central goal of our lab at ISC. We try to understand how the brain solves vision. And the flip side is, of course, we'll understand how computers don't solve vision. Maybe we can make them solve vision if we understand how the brain does it. We try to do this using a number of different types of experiments. These are human experiments where we look at behavior, we look at brain imaging, we also are looking at perception in adults. More recently, we're looking at how children learn to read, because new brain regions are formed when you learn to read. To understand this at the more cellular and finer grain levels, we are performing experiments with monkeys, and this is because their brains and vision is very similar to ours. We're looking there at behavioral neural activity. We are looking at how animals perceive visual information. We're looking at how these animals make decisions and so on. And a core theme that unites all of these things is computation. That is, we are trying to understand our data by building models of the data and then comparing computational models or computer vision models with the brain. So how does the brain solve vision? Well, it turns out even the brain finds vision to be a hard problem, because if you look at the amount of real estate occupied by vision in the brain, almost 40% of your brain is involved in vision of one kind or the other. And that's a huge amount of brain space for a very tiny part of your body. And that's because vision is a hard problem. It's an interesting problem, and the brain also finds it non-trivial to solve it. And part of the reason we're not aware of the difficulty of the problem is because the brains have evolved to solve the problem of vision over the course of evolution, and we're just not aware of all the processing that goes on of our visual information. So interestingly, when there is damage to various parts of the brain that are processing visual information, you can have very specific disorders where the eyes are okay, but perception is not okay. So one example of it, which we are very excited to start, is what we're calling the Indian Face Perception Project. And it turns out there's a condition called, of course, all of you know about color blindness. There is a condition called face blindness, where people with this condition have a lot of difficulty recognizing faces. And this is because of some kind of abnormal processing they have of either faces or objects or in general visual information. We don't know the reason. There is also another group of people who are super recognizers. They are actually really good, much better than normal in recognizing faces. And again, we don't understand how their face processing is better than all of us. And our goal is to try and understand this full range of face abilities. And I'm not going to talk about this project. We've just started this project. Please Google if you're interested to find what we're doing on this front. We're also looking at reading in children. And so this is of course an extreme condition where people are unable to read. Children have this condition called dyslexia sometimes. And this is a problem of both sound and language processing as well as visual processing. And the visual processing component of it is very poorly understood. And so we are doing some research, and more recently we are partnering with schools and nonprofits to try and understand what predicts when children learn to read fluently versus what predicts when children cannot read fluently and have lots of reading difficulties. But this is all about just a general overview. What I want to tell you about is two components in this talk. It's a bit ambitious. I'm not sure I'll go through both of them. But one component is using monkey brain recordings to understand how vision works in the real world. And the second is using human brain imaging and behavior to understand sort of novel computations that our brain is doing. So hopefully I'll go through both. So let's start with the first one. The traditional approach to understanding brain activity in animals, and especially smart animals like monkeys, is to actually bring them into the lab. And so if you want to get brain activity from an animal, you've got to kind of restrain it, you've got to bring it into a lab, make it do some task. And if you're if you're interested in studying vision, you've got to actually present stuff on the screen and they got to look at it, you need to monitor their gaze, and it's a pretty complicated setup. And actually there's a lot of different components that happens. But one thing you might be struck by, if you have never seen something like this before, is that while this may be a very interesting and sort of useful way to get information about visual processing in the brain, it's actually blinding us in a sense, because you don't know how the brain behaves in the natural world. And if you look at the 99% of vision studies which are done both on humans and animals, they're all stuff where you present stuff in front of a screen. And so one of the things that we started to do a couple of years ago is to say, well, can we actually flip this entire approach? And actually, can we study natural vision? And the vision there is to bring the lab to where the animal is. That is, in other words, bring your neuroscience to where the ecologically valid and natural conditions. But this is much, much easier said than done, because there's a lot of barriers to cross, and you can get to very uncontrolled settings where you may not be able to understand and interpret brain activity because it's natural behaviors. So we had to shed a lot of things. So for example, we need to understand and track where animals are looking at in unrestrained settings. You've got to train animals in a natural setting. You've got to also do wireless recordings, and this is really crucial, because if you think about it, if you're getting information out of the brain, some wire has to go out, and unlike rats, which may not do this, monkeys will just yank the wire. And so you need to have a way of wirelessly recording information, and this is again easier said than done. There's lots of power issues, electronic issues and all that. So this is the dream team, sort of like the Ocean's 11. We're trying to understand whether we can understand brain activity in natural vision. So one question to start out with, this is sort of our monkey lab. One question that we started with saying, is it enough to just record brain activity in a natural setting, or do you need something else? Well, what we realized is that you need to have a control setting where you can record brain activity over many, many trials, because natural behavior is highly variable, and so you may not be able to interpret what you're seeing in natural behavior unless you are able to record from the brain in a more controlled setting. So we built a lab like this, which is kind of a hybrid of two settings, where the animals actually live here. It's kind of like a 5-star hotel in a very naturalistic kind of setting. They commute through a series of doors where we don't touch them, we just kind of open doors to let them in. And then they come to a workstation very similar to ours, where we interact with stuff on a screen, and then we get some juice rewards or money rewards. In the case of our monkeys, they get a juice reward. And so basically they come here, perform some tasks and get a juice reward. There's a pretty complicated setup behind this, because you've got to track where they're looking, and you've got to be able to train them on complex tasks. There's a lot of interesting anecdotes and things I can tell you offline, but basically this is the entire system. And so then you might be wondering, what do you train these animals on? So what we decided to train these animals on is a kind of fundamental cognitive task, which I think is very interesting, because it gives you sort of windows into how the brain works at different points in the task. So here's an example of the task. Basically, the task starts with the green button. The animal has to touch the green button to initiate the task, and then a sample appears and disappears after some time. And then two choices appear. So in one trial, the same object could repeat. In another trial, some other object could be shown. And the animal's task is to indicate whether the two objects that are shown are the same or different. Okay? So if they're the same, he has to press the top button, and if those two objects are different, he has to press the bottom button. So why is this an interesting task? Well, if you think about the brain activity that's evoked when you look at the object for the first time, that's just a probe for the basic visual response. It's a sensory response that's coming in. The animal just needs to hold this item in memory. Now, if you look at the delay period, the item to be remembered is gone. So there is some brain activity that the animal has to create to be able to remember that item in memory. And then the third phase is kind of a probe for decision making, because the animal has to now match what he's looking at on the screen with the content of what was in his memory. And so this is a very basic kind of cognitive task where we can probe a lot of interesting aspects of cognition. Okay, so let me show you a video. This is a video of one of our animals that performed the task a couple of years ago. So he's looking around because it's a free setup. So the animal has to do the task for getting juice. And eventually he'll say, okay, I'm going to look at the screen. And the key innovation that we had here, this is completely custom built around the animal. So the key innovation that we have here is that there's a chin rest. And so the animal has to put his head in exactly one particular position, which standardizes his eyes, and therefore we can track the gaze of the animal. And so in tasks like these, you can see the animal is actually doing the task that I told you. He's looking at 2 items. When the 2 items are the same, then he presses one button. If the 2 items are different, he presses another button. And then when he makes a correct response, he gets juice reward. And if he does a wrong response or moves away, he doesn't get anything. Okay, so there, for example, he's taking a break. He can do whatever he wants, but he won't get juice. And so ultimately, he wants juice, so he'll do the task. And they like this juice, so they'll do the task. Okay, so that's the setup. Okay, and where do we record from? And this is again a question that we wanted to do. What we're doing is to record from 2 key regions. One is a higher level visual cortex. This is the final stage of the visual processing pathway in the brain. This region is very important because if this region is damaged because of stroke or any kind of condition, you'll have severe difficulties in recognizing objects. So we know that this region is very important for object recognition. The other region that we are also recording from is the premotor cortex, where we think decisions about any task are formed. And so this decision is being made in the motor cortex. So we want to understand how the visual information in the visual cortex goes off and becomes a decision in the motor cortex. Okay, so that's the overall setup. So let's run through a couple of questions. I don't have time to go through a lot of them, but the basic enterprise is like this. First of all, will this even work in a simple task? Okay, so what's the most simple task we can imagine? And we'll run that. And the second is, will it help us understand sleep? And this kind of an interesting connection between what Nitin just talked about. So let's start with the simplest task possible. What's the simplest task that you can think of in a natural environment? Well, the task that we thought of is that simply a human experimenter will walk into the room where the animal is and hand over a piece of fruit to the animal and then come back. Okay? So what do we think might be happening during this task? Well, first of all, bunch of things happening. The animal has to look at the experimenter. He looks at the food that's being offered. The animal takes the food and all that. So that's a basic proof of concept for us. So this is many trials of the task I'm showing you here. There are 2 different experimenters and there are 3 different types of food. The 3 foods are raisin, carrot and banana. So we call this the RCB experiment. Okay, and this was also a successful experiment actually in this case. Okay, so what's going on here is that we also made an experiment where the animals looked at images on the screen. Okay, so we have brain activity recorded while animals are looking at images on the screen. And what we do is to build linear classifiers which look at the pattern of activity which is evoked by each particular object. So for example, I'm showing you the raisin, carrot and banana. These are the boxes that were actually shown to the animal in the experiment. But we're taking images of those boxes and showing those objects on the screen and building a pattern classifier which will tell us if you look at when you look at the brain activity in the real world, we can then classify whether the animal is looking at the experimenter or the food and so on. So the idea is you train on the screen and then you test it in the real world. And if it works, then we've established a kind of systematic bridge between the natural setting and a kind of more controlled setting. But first of all, you've got to do a sanity check. So sanity check is, well, let's take new trials in the screen-based task and just check whether we can decode the identity of an experimenter or the identity of food that is shown on the screen. So that's exactly what we did. So the animals are just looking at these food images and experimenter images. Those are images of a few of the students who are doing the task. Then this is just the decoding type. So basically what we're doing is using neural activity to guess the identity of the food being offered, or the food being shown on the screen, or using neural activity to guess the identity of the experimenter that is actually shown on the screen. So this is all screen based. So obviously we are able to do this. This is just a sanity check. The ultimate test is of course what's happening in the natural task. And it turns out that we're able to decode food and experimenter identity correctly above chance. So we think that there's a systematic link that we're able to get between neural activity on a screen to neural activity in the real world. So will it work in a simple task? The answer is yes. This may be kind of, maybe you're wondering, well, this is pretty obvious. But what we are showing is the degree to which there's a generalization. So I mean, yes, it stands to reason that things that you show on a screen should generalize to the natural world. But in the natural task, there's lots more other influences on the brain activity. And despite the fact that all of those other things are happening, we still have a systematic relationship between the screen-based activity and the real world. So let me show you a couple of things about sleep. The big advantage of our setup is that now we can record from brain activity under any condition. So for example, the animal is taking a break. I can record brain activity and say, well, can I predict that he'll take a break? There's a naturalistic environment, so I can also record from the animals when they're sleeping. So can we understand sleep? And this is probably one of the very few studies that have been done with primates sleeping. Here's a screenshot. This is actually an infrared image of our animals, the animal in the sleep condition and the wake condition. Very interestingly, monkeys don't actually lie down to sleep, unlike us. So they actually crouch and they sleep like that. And so by looking at their body posture and the fact that their eyes are open or closed, we can tell that they're sleeping or not. We don't have rapid eye movements that we can monitor because the animals are in a natural setting, so we don't have eye movement tracking like that. Okay, so here's a snapshot of brain activity that we've recorded now from both animals. What you can see, the orange patches are the times when the animals woke up. So just like us, they kind of wake up in the middle of the night, they move around a bit, or they move a little bit during the sleep and so on. And so we annotated all of these based on the videos. And the brain activity is just given you as a sample. So the first question we wanted to ask is, well, given the brain activity in the visual cortex or the motor cortex, can I actually tell if the animal is sleeping or not? So what do we do? Again, it's basically a pattern classification approach. So what we're doing is to train classifiers on the brain activity, which is recorded during the wake state and the sleep state. And then we're saying, given a new epoch of activity, can I predict if the animal is sleeping or awake? And turns out that we can do this better than chance. But what's more interesting is that we can also predict the onset of sleep or wake states. So in other words, if you now plot the probability of the classifier or the accuracy of or the probability of decoding of the classifier around the time of when the animal is going to wake up or when the animal is going to go to sleep, what you can see is that these classifiers seem to predict when the animal is going to wake up and when the animal is going to go to sleep. And that's kind of making sense because you can imagine if you were going to sleep, your motor movements would slow down, your vision would change a bit because you're kind of closing your eyes. So there is sensory and motor consequences of entering a sleep state and also exiting a sleep state. So that all this makes sense. But what was more interesting for us, and what you're probably thinking of right now, is can we understand something about dreams? Okay, and turns out we can, kind of. So here's how it goes. So what we did was, clearly the pattern of neural activity during the wake state and the sleep state is quite different. So because I can decode the pattern that is occurring in the brain. So then what we did was, for every epoch of neural activity, for every epoch of the whole sleep session, we can characterize a similarity between the wake state and the sleep state. And so what we're plotting here is the similarity between the brain activity recorded at every moment in time to a template wake state and a template sleep state. And so there are periods that we've highlighted in orange, which are of course the wake states, and the blue are the sleep states. But what we noticed was there was a couple of times during the sleep state where the neural activity was very much like the wake state. And that became an indication for us that maybe this is kind of like a REM sleep or dream phase, because this is known from the literature in humans and animals that there is a kind of REM phase that people go through. So we thought, okay, this is interesting. This is a REM phase that we can identify during the sleep recording. And so what we did was the same animals were shown these pictures of these food and boxes with food and without food. So we can train a classifier that tells us whether the pattern of activity in the animal's brain is similar to when it's looking at food versus when it's not looking at food. And so what we did was, we know the brain activity in the awake state when they're looking at images on the screen, and then we are trying to decode what's happening in the sleep state based on these decoders. Okay, so that's the idea. So the hypothesis was, well, monkeys should be dreaming about food, right? And so then we said, okay, if monkeys are really dreaming about food, then the activity corresponding to when they're actually looking at the food should correspond to when they're actually dreaming about food. And so we look at the probability of the classifier to actually indicate the presence of food. So what I'm plotting on the y-axis is the probability of food as deduced from the wake state responses, right? And so what I'm simply saying here, during the NREM phase, that is normal sleep, versus the REM state versus the awake state, what is the probability that the classifier says that the animal is thinking about food? And it turns out that in the REM state, as you kind of might expect, there's a higher probability that the pattern of activity in the brain resembles the activity that you're looking at food. You could do the same experiment on faces. You could say faces versus other objects or objects versus other things, and those classifiers don't show you the same pattern. It suggests that whatever activity is being instantiated during the REM state is probably specific to food, and that kind of makes sense. Okay, so that's this part, and I think I will try to rush through the second part as well. So this is all about understanding real world vision. I've shown you some snippets of what we're able to find. Let me show you quickly a kind of concept of what we can do with human studies as well. So if you think about doing visual tasks, right? Here's a nice photo of our department during one of our events. And if you're looking for my face, then you're probably looking for specific features. I mean, you can look for the absence of hair, and that'll shortlist, that'll give you a short list of people to look at. But usually when you're looking for a particular, in a visual task, you're usually looking for specific features. But it turns out that we also do a lot of visual tasks which involve not looking for features. Okay, so for example, there are many tasks where we are looking for properties. So let me give you an example. I can show you these two images, and you can easily tell that the two items that are shown in the top row are actually same, and you can easily tell that these two items are different, right? You can also do a task where you're looking for the odd one out, and you can see that in the bottom array, there's an odd one out. On the top one, there's no odd one out, right? You can also do this task of detecting if an object is symmetric or not, right? So if you think about how you're doing these tasks, there is no feature I'm actually specifying for you. So how is it that you're actually doing the task? What feature are you even using? Because all of these tasks do not involve looking for any feature, but rather looking for a property in the image. So the question is, how do you look for properties in images, right? And if you're thinking that this is some sort of obscure lab-based task, I would argue that we do this kind of task all the time, more often than you would imagine. So for example, if you look at this image, you immediately know that it's Barack Obama. And you see a particular face in multiple different conditions, wearing different kinds of clothes and all that. And the fact that you're able to tell that it's the same person and not a different person is that you're actually solving a same different task. Okay? You could also be looking at two animals from the same animal from different viewpoints. And again, you got to extract the features that actually help you recognize it's the same animal. These are, of course, not just about spotting differences, and there's all kinds of folk psychology built around all of these things. We also value symmetry. So again, when we look at beautiful temples like these in Karnataka, the aesthetic experience of symmetry is what gives you that aesthetic appeal to these things. So these are all not sort of lab tasks, and they have some relevance to the real world. So I'll just leave you the question of how do we actually solve this task. So for example, if you're looking for my face, then you're looking for some kind of similarity, and you can draw some boundary. And this is a standard approach of machine classification. There's a pattern or a feature to look for, and so you can draw a boundary, and then you found the feature. But then if it's a generic task or a property-based task, well, what's the feature space, and what's the decision variable? What are you actually using to detect the features? So let me give you just a brief glimpse, because I'm almost out of time. So this is the idea. The question is, how is the brain representing multi-item arrays? Turns out that we know a little bit about it. If you imagine that there are two cells in your brain, not to insult you, of course, there are many more cells in your brain, but if you have two cells in your visual cortex and they're responding differently to different images, you can imagine the response to those three images are something like that. Now we know that in the visual cortex, if you show multiple items, the response is an average of the item responses. So if you're looking at the response to the 4 monkey images, then the response is going to be just the average of those. And similarly for the horse, similarly for the dog. I'll just take a minute to sort of wrap up the idea. So what we realized is that if you're looking at pure arrays which have no odd one out, the response is going to be exactly the same as the single item responses, because you're just doing an average. Your brain is doing an average of the response. But if you're looking at items which have one odd one out, what's going on? Well, it turns out, if you think about it's true even in a vector space, if you're taking the average of the neural activity of 3 horses and 1 monkey, then the response is going to be on the line joining the horse and the monkey. Okay? And the way it will determine how much the response is closer to the horse or closer to the monkey. And so if you think about it, all these odd one out arrays are actually kind of in the middle, all those red triangles. And if you're measuring the distance of each of those arrays from the center, you'll notice that all the arrays that are actually containing odd on out are actually kind of closer to the center, and all the arrays that don't contain the odd on out are actually far away from the center. And this is the essential principle of homogeneity, which is that it's just like mixing paints. If you mix red paint with slightly off red paint, you'll still get red. But if you mix a bunch of paints, you'll start getting everything brown, right? And so that's exactly what is happening with these things. And we think the brain is computing some sort of distance from the center to solve the task. And I'll sort of stop there because I'm out of time. And thank you for your attention. And I'm happy to take questions.
Questions?
Thank you so much for a very interesting talk. So I have two questions. The first one is, what do you exactly mean by brain activity? It must be an n-dimensional feature. So what are those features? Yeah. And secondly, what is the decoder architecture you're talking about?
So the brain activity in our case is we're recording voltage fluctuations from the extracellular medium by inserting electrodes into the brain. And so the number of electrodes determines the dimensionality of the brain activity. So if, for example, we're recording from 128 electrodes, which is the case in our case. So we have 128 numbers that you can extract at any given moment in time, which reflect the amount of brain activity which is going on at that moment in time. So for example, if you're counting action potentials, then this number of action potentials in a small time window. And so that's the dimensionality. And the classification that we use is basically linear classifiers. So we're just using linear discriminant analysis. And it's been shown, interestingly, that even if you use more sophisticated classifiers like machine learning or SVMs and so on, the classification accuracy doesn't increase too much. In fact, it doesn't increase at all. And so that's given rise to this idea that the brain is trying to encode information such that the information is linearly separable, so that you don't have to spend a lot of effort in classification, rather than you would rather invest all that effort in feature processing. That seems to be what the brain is doing.
Thank you so much.
Sir, you place the electrodes in the probably in the inferior temporal gyri. Yes. But in human being, I think the visual cortex is in the occipital lobe.
That's right. That's right. So that's one very important and interesting difference between the monkey visual cortex, where the visual processing in the monkey goes all the way down to the pole of the temporal lobe, whereas in the human, it only goes up to the occipital lobe, and the temporal lobe is actually involved in language and object naming and all that. There is still a visual response, but it's still mixed with language. Yeah. So that's part of the reason why in humans we don't really understand the functions of the temporal lobe very well, because those are kind of association areas. They're intermediate between vision and language. All the reading areas that are formed are in the temporal lobe and so on.
Yeah, so is there a question there? Okay. So I was just curious about where do you get like the monkeys from? Like, do you farm them or do you like pick them from?
We have a primate facility here since many years, and
right.
The animals are actually housed, and also it's a breeding colony, so we breed them.
I see. So in that case, just to follow up, like, do you think the decision making for the individuals which are like brought up in the setup compared to the ones in the natural environment would be different?
It's a great question. It's very difficult to answer also,
right.
Because
I
test
think
them in some way, and testing them will require some training.
Right. Because in the natural environment, I think there would be more factors which would lead to their decision making, right?
That's right. In fact, not just that. Even if you take them from this very controlled setup, like in front of a screen, to a naturalistic setting, even that opens up all kinds of extra brain activity that's happening.
Right.
It makes it very difficult to interpret even there. So yeah, I do agree with you. I think one must go in some. You've got to push systematically along the way.
Right. Yes. Thank you so much.
Okay, I know some people had more questions. I urge them to catch the speaker at lunch. I'd like to thank the Academy for hosting this symposium, and thank you all for being here.
Okay, so I would just like to reiterate what Shona just said. It's been a great pleasure, and I hope everybody enjoyed all the talks of the meeting. And of course, the symposium, I hope, was enjoyed by everybody. It was a sort of theme symposium that we put together. I would like to invite everybody for the next meeting, the annual meeting, which will be held from 14th to the 16th of November at ISER Tirupati. And again, we hope to have a whole set of exciting talks and look forward to seeing everyone there. Thank you. With that, I'd like to formally close the symposium.